Imagine a mysterious force, one that bends the very fabric of space, creating a hidden world where objects vanish from our sight. This isn't some science fiction tale, it's a real phenomenon, one that challenges everything we thought we knew about gravity and the universe. It's called gravitational shadowing, and its effects are mind-bending in their complexity. How is it that something so fundamental, like gravity, can cause light and matter to disappear into an invisible void? What does this tell us about the cosmos and the nature of reality itself? Let's dive deep into this intriguing topic. But before we continue, subscribe to the channel so you don't miss out on any of these videos. Gravitational shadowing, at first glance, may seem like just another quirky feature of our universe. But the more we understand it, the more we realize that it holds the key to some of the most profound mysteries of space. This effect is intimately tied to the concept of gravitational lensing, which was first predicted by Einstein as part of his general theory of relativity. But while gravitational lensing bends light, creating beautiful cosmic phenomena like Einstein rings, gravitational shadowing takes things a step further. It's the idea that gravity, with its immense strength, can actually cause entire regions of space to become hidden or shrouded, blocking our view of celestial objects behind them. The core concept behind gravitational shadowing comes from understanding the relationship between gravity and light. Light, the fastest thing in the universe, doesn't always travel in a straight line. When it passes through regions of intense gravitational fields, like those near black holes or massive stars, it bends. This is known as gravitational lensing. But what happens when the gravitational pull is so strong that it not only bends light but effectively shields objects from view entirely? This type of phenomenon occurs when an object, usually a very massive one, warps the fabric of space-time to such an extent that it creates a shadow, one so profound that even light can't escape its grip. To visualize this, think of how the moon casts a shadow on Earth during a solar eclipse. In the cosmos, however, these shadows are far more complex and stretch across unimaginable distances. One of the best-known examples of gravitational shadowing is the event horizon of a black hole. When light gets too close to a black hole, it is trapped by its gravitational pull. The point at which light cannot escape is known as the event horizon, and anything that crosses this boundary is effectively hidden from the rest of the universe. But the event horizon is just one manifestation of gravitational shadowing. It's a dramatic one, yes, but it's not the only place where this effect occurs. There are also more subtle forms of gravitational shadowing scattered throughout the cosmos. For instance, large clusters of galaxies, with their combined gravitational forces, can cast shadows over the background universe. These massive cosmic structures, called galaxy clusters, are so dense that they warp the space-time around them, bending the path of light from objects lying beyond them. In a sense, they create regions of the universe that are obscured from our view, making it harder for astronomers to map the farthest reaches of space. But what's even more interesting is that these cosmic shadows don't just block our view, they can provide new insights into the structure of the universe itself. In recent years, astronomers have used gravitational shadowing to uncover some astonishing details about the unseen universe. By studying how light is distorted as it passes through the shadows of massive structures, researchers can learn more about the distribution of matter in the universe, especially the dark matter that remains invisible to traditional observation methods. This method, known as gravitational lensing, has allowed scientists to map the hidden mass of galaxy clusters and gain a deeper understanding of the mysterious force that makes up most of the universe's mass. One fascinating aspect of gravitational shadowing is the way it can hide objects from view, effectively creating what is known as gravitationally induced invisibility. Imagine a star or even an entire galaxy that's hidden from our line of sight because its light is being bent around an intervening massive object. This could mean that there are entire cosmic structures lurking just beyond our vision, existing in regions of space we can't detect, yet they are there, influencing the surrounding universe in ways we can't fully comprehend. But gravitational shadowing isn't only limited to massive celestial bodies like black holes and galaxy clusters. It also plays a role in the formation of other cosmic structures. For instance, during the early stages of the universe, gravitational shadowing likely contributed to the formation of large-scale structures like superclusters and voids. The distribution of matter and energy in the universe wasn't uniform, and gravitational shadowing helped shape the way galaxies and clusters formed by masking certain regions of space and enhancing others. So, how does this impact our understanding of the universe? Gravitational shadowing suggests that the universe is far more complex than we previously thought. It challenges our perceptions of visibility and makes us rethink what is possible in space. The concept also poses fascinating questions about what might be lurking in the shadows of the cosmos, waiting to be uncovered by future technologies and scientific breakthroughs. Could there be entire galaxies or even other universes hidden behind the gravitational curtains of larger, unseen objects? As we advance our understanding of gravity and light, gravitational shadowing may become one of the most powerful tools for unlocking the mysteries of the universe. As intriguing as it is, gravitational shadowing doesn't just point to hidden cosmic phenomena. It also has practical applications in the realm of astrophysics. By studying how light behaves when it passes through these gravitational shadows, scientists can make more accurate measurements of the mass and distribution of objects in space. This is particularly important when studying the elusive dark matter that constitutes most of the universe's mass. By using gravitational shadowing as a tool, researchers can gather indirect evidence of dark matter's existence, even though it doesn't emit light or other forms of radiation. Beyond dark matter, gravitational shadowing might also offer clues about the nature of gravity itself. While we know that gravity is a force that attracts objects with mass, it's still one of the least understood forces in physics. By studying how light is influenced by gravity in extreme situations, scientists can test the predictions of general relativity and potentially discover new aspects of the force that we haven't yet observed. One fascinating experiment in this field involves using gravitational shadowing to probe the inner workings of supermassive black holes. These cosmic giants, which exist at the centers of most galaxies, are some of the most extreme environments in the universe. By observing how light is bent and obscured by the immense gravitational pull of a black hole, researchers can gain insight into the behavior of matter and energy near the event horizon. These observations could help us understand the fundamental physics of black holes, potentially leading to new breakthroughs in our understanding of space and time. In the future, as our technology advances, we may be able to observe even more subtle forms of gravitational shadowing. For example, upcoming space telescopes could detect cosmic shadows that were previously undetectable with our current tools. These observations could revolutionize our understanding of the universe, providing us with a clearer picture of its structure and the forces that govern its behavior. What's particularly fascinating about gravitational shadowing is the way it challenges our conventional understanding of how light behaves in the universe. In everyday life, light travels in straight lines, and we can usually see everything within our line of sight. But when we look at the cosmos through the lens of gravitational shadowing, we realize that light doesn't always obey these simple rules. It bends, it curves, and sometimes it vanishes entirely, creating an intricate web of cosmic shadows that obscure our view of the universe. This new perspective invites us to reconsider everything we thought we knew about space and time. It suggests that our understanding of the cosmos is still in its infancy, and there is so much more to discover. Gravitational shadowing is just one of many phenomena that point to the fact that the universe is far more mysterious and complex than we can imagine. And as we continue to explore these hidden corners of the cosmos, who knows what other incredible discoveries await us? Gravitational shadowing is not just a fascinating aspect of astrophysics. It also highlights the extraordinary potential for future discoveries that may reshape our understanding of the cosmos. As technology continues to evolve, we find ourselves on the verge of breakthroughs that could unlock secrets that have eluded scientists for centuries. With advancements in space telescopes, observational instruments, and computational models, researchers are poised to study gravitational shadowing with more precision and insight than ever before. One of the most promising areas of study involves the ongoing efforts to observe gravitational waves, ripples in space-time caused by massive objects like black holes or neutron stars. These waves travel at the speed of light, carrying with them information about the most violent events in the universe. While gravitational waves themselves are not exactly a form of shadowing, the phenomenon is closely related, as both involve the bending and warping of spacetime itself. By combining observations of gravitational waves with those of gravitational shadowing, scientists can develop a deeper understanding of how these massive objects interact and influence the surrounding universe. Moreover, as our ability to detect exoplanets, planets orbiting stars outside our solar system, improves, we may begin to see more instances where gravitational shadowing plays a role. In some cases, exoplanets and their parent stars may be hidden behind massive cosmic objects, creating regions of space where we cannot see them directly. But by studying the gravitational interactions between these objects, astronomers could indirectly observe the hidden exoplanets, gaining insights into their composition, size, and even the potential for life beyond Earth. Additionally, another exciting aspect of gravitational shadowing lies in its implications for the study of the multiverse. The idea of parallel universes, or a multiverse, has long been a topic of speculation in the world of theoretical physics. If other universes exist, it's possible that gravitational shadowing could provide the key to detecting them. Some theories suggest that the immense gravitational forces of black holes or other large objects could cause windows into these parallel universes, creating shadowing effects that might leave subtle, detectable traces in the cosmic fabric. While still speculative, this possibility opens up tantalizing possibilities for future discoveries that could fundamentally alter our understanding of reality itself. Another interesting facet of gravitational shadowing is its potential to reveal hidden structures in the universe. We are accustomed to seeing stars, galaxies, and nebulae through the lens of visible light, but much of the universe remains obscured from our view due to dust, gas, and other matter that scatters or absorbs light. Gravitational shadowing, however, might allow us to peer through some of these obstructions, offering glimpses of objects and structures that would otherwise remain hidden. For instance, regions of space that are shrouded by gas clouds or dark matter could be studied in greater detail by examining the way light is distorted as it passes through these regions. This could help uncover previously undetected galaxies, clusters, or even exotic phenomena that we currently cannot observe with traditional methods. To further explore the idea of hidden structures, it's important to consider the role of dark energy in gravitational shadowing. Dark energy, the mysterious force thought to be responsible for the accelerated expansion of the universe, is one of the most perplexing concepts in modern physics. While its effects are observable on large scales, it remains poorly understood. Some theorists speculate that dark energy could be responsible for creating regions of space where gravitational shadowing is particularly pronounced, hiding entire regions of the cosmos from view. If this is true, understanding dark energy could not only provide insights into the universe's expansion but also allow us to better understand how gravitational shadowing works on even larger, cosmological scales. Moreover, gravitational shadowing may also play a significant role in the formation of cosmic structures. The way galaxies, stars, and planets are arranged throughout the universe is heavily influenced by gravitational forces. As massive objects warp spacetime, they can shape the paths of smaller objects, guiding them into clusters or voids. Gravitational shadowing may further complicate this process by creating invisible barriers that can alter the trajectories of objects, causing them to form in unexpected ways. Understanding these dynamics could provide valuable insights into the evolution of galaxies and the large-scale structure of the universe. As our knowledge of gravitational shadowing expands, it's clear that this phenomenon is more than just an interesting quirk of space. It's a fundamental aspect of how the universe operates, and it has the potential to unlock some of the most profound secrets of the cosmos. From the hidden masses of dark matter to the behavior of light around black holes, gravitational shadowing offers a unique lens through which we can observe and understand the universe. It challenges us to rethink our basic assumptions about space, time, and light, urging us to look beyond what we can see with our eyes and explore the invisible forces that shape our reality. One of the most exciting prospects of studying gravitational shadowing is the potential to observe phenomena that were previously thought to be beyond our reach. For instance, We might be able to detect objects that are currently invisible to us, such as dark matter or even entire galaxies that have been hidden behind massive structures. These discoveries could not only expand our understanding of the universe but also provide new clues about the fundamental nature of reality itself. The more we study gravitational shadowing, the more we begin to appreciate just how much of the cosmos remains unexplored, hidden from our view in the shadows cast by the immense gravitational forces of the universe. As technology advances, so too does our ability to peer deeper into the cosmos and observe the subtle effects of gravitational shadowing. With the launch of new space telescopes, such as the James Webb Space Telescope, and the development of advanced computational models, we are poised to uncover new insights into this phenomenon. The future of gravitational shadowing research is bright, and as we continue to unravel the mysteries of space, we may find that we've only scratched the surface of what's possible. Gravitational shadowing is a reminder that the universe is full of hidden wonders, waiting to be discovered. Whether it's the invisible influence of dark matter, the elusive nature of black holes, or the potential for hidden cosmic structures, this phenomenon challenges our understanding of the cosmos in exciting and profound ways. As we continue to push the boundaries of science and technology, there's no telling what other mysteries gravitational shadowing will reveal. What we do know is that the universe is far more intricate and mysterious than we could have ever imagined, and that's what makes studying gravitational shadowing such a fascinating pursuit. Gravitational shadowing not only piques our curiosity about the vast and invisible structures in the universe but also fuels our search for new theories that could explain the complex interactions happening within these shadowed regions. As our tools improve, we find ourselves on the cusp of breakthroughs that could deepen our understanding of both fundamental physics and the hidden fabric of spacetime itself. Perhaps one of the most exciting aspects of gravitational shadowing is its potential to reveal new types of cosmic objects that we have never seen before, objects that could change the way we view our place in the universe. One intriguing theory that might be influenced by gravitational shadowing is the concept of gravitational lensing. This effect occurs when light from distant stars or galaxies is bent by the gravitational pull of a massive object, like a black hole or a galaxy cluster, that lies between the light source and the observer. Gravitational lensing has been used by astronomers to study the distribution of dark matter and to detect galaxies and other objects that would otherwise be hidden from our view. However, gravitational shadowing could provide additional insights by offering a new perspective on the way these objects behave. By studying the precise effects of gravitational shadowing, we could refine our understanding of gravitational lensing and learn more about how massive objects distort the fabric of spacetime. The connection between gravitational shadowing and black holes is particularly fascinating. These mysterious objects, whose gravitational pull is so intense that not even light can escape, are already known for their extraordinary ability to distort spacetime. But could there be more to black holes than we currently understand? The way gravitational shadowing affects the region around a black hole could hold the key to unlocking some of the most puzzling aspects of these cosmic giants. For example, recent studies suggest that there may be shadow regions around black holes, areas where light is entirely blocked by the intense gravitational forces. These regions could offer a wealth of information about the inner workings of black holes and help resolve some of the paradoxes associated with them, such as the information loss problem. Furthermore, the impact of gravitational shadowing could extend to the study of galaxy formation. It's well established that galaxies form as matter collapses under its own gravity, but the role of gravitational shadowing in this process is still not fully understood. Could gravitational shadowing help shape the way galaxies evolve? By studying the distribution of light around galaxy clusters, researchers may be able to trace the subtle effects of shadowing that influence the movement of gas and dust in these regions. This could offer a new lens through which to study the birth and growth of galaxies, providing clues about the forces at play in the universe's most fundamental structures. Gravitational shadowing is also poised to offer insights into the long-standing mysteries of dark matter and dark energy. These elusive components make up the majority of the universe's mass and energy, yet their true nature remains one of the biggest unanswered questions in modern physics. Could gravitational shadowing be the key to unlocking the secrets of dark matter? Some theories suggest that dark matter might be composed of particles that interact very weakly with light, making them invisible to our current observational methods. However, their gravitational effects can still be detected. By examining how gravitational shadowing alters the light around dark matter-rich regions, we could gain a better understanding of its distribution and properties. Similarly, dark energy, the mysterious force driving the accelerated expansion of the universe, could be linked to gravitational shadowing in ways we haven't yet realized. As dark energy influences the expansion of space-time, it might also play a role in creating regions where gravitational shadowing is more pronounced. This could open up new ways of studying dark energy and its effect on the structure and evolution of the cosmos. It's an area of research that is still in its infancy, but one that holds incredible promise for advancing our knowledge of the universe's fundamental forces. While the theoretical aspects of gravitational shadowing are exciting, the practical implications for space exploration and observation are just as compelling. As we develop more sophisticated telescopes and space-based instruments, we may be able to directly observe the effects of gravitational shadowing in a way that was previously impossible. One area where this could be particularly useful is in the study of exoplanets, planets that orbit stars beyond our solar system. Many of these planets are located in regions of space that are difficult to observe due to their distance, or the presence of other massive objects in the vicinity. Gravitational shadowing might help reveal these hidden worlds by bending light in ways that allow us to detect their presence. In addition, gravitational shadowing could play a role in the search for extraterrestrial life. While the search for life beyond Earth has traditionally focused on finding planets with conditions similar to our own, gravitational shadowing might uncover new habitats in the far reaches of space. By studying the gravitational effects on light passing through distant regions, astronomers could identify planets that were previously undetectable, expanding the pool of potential candidates for the search for alien life. This is an exciting prospect, as it suggests that there could be more worlds out there than we ever imagined, and many of them may harbor the conditions necessary for life to thrive. Gravitational shadowing may also offer new insights into the behavior of cosmic dust and gas. These particles play a crucial role in the formation of stars, planets, and galaxies, but their behavior is not fully understood. By studying how gravitational shadowing affects the movement of these particles, scientists could gain a better understanding of the processes that govern the formation of celestial bodies. This could have far-reaching implications for our understanding of star and planet formation, as well as the broader evolution of galaxies. As we look to the future, the study of gravitational shadowing will undoubtedly continue to play a crucial role in our exploration of the universe. With new technologies and techniques on the horizon, we are likely to uncover even more hidden aspects of the cosmos that were once beyond our reach. Whether it's through the study of black holes, dark matter, exoplanets, or the fundamental forces of nature, gravitational shadowing offers a fascinating and continually evolving frontier of scientific discovery. And as we uncover more about this mysterious phenomenon, we may find that the universe is even more complex and awe-inspiring than we ever imagined. The deeper we dive into the concept of gravitational shadowing, the more we realize just how profound its implications can be, not just for astronomy but for our broader understanding of the universe. Every new discovery opens more questions, suggesting that the universe is infinitely complex and that we are only scratching the surface of what is possible. As technology continues to advance, we will likely find new ways to observe phenomena that we never thought we could detect. A particularly exciting frontier in the study of gravitational shadowing involves the use of quantum mechanics to explain some of the more subtle effects that we observe. Quantum theory, which governs the behavior of particles at the smallest scales, might provide new insights into how gravitational forces operate in extreme conditions. In many ways, gravity remains one of the least understood forces in quantum mechanics. Unlike the electromagnetic, strong, and weak nuclear forces, gravity has resisted unification with the quantum world. Some scientists believe that the study of gravitational shadowing could offer new clues about how gravity operates on the smallest scales, potentially leading to a theory of quantum gravity that can explain both the large-scale forces of the cosmos and the fundamental particles that make up everything. One area where this connection between quantum mechanics and gravitational shadowing is particularly interesting is in the study of black holes. Black holes, as we know, are incredibly dense regions of space where gravity is so strong that not even light can escape. The study of gravitational shadowing around black holes might offer the key to understanding the behavior of these mysterious objects. For instance, there has been ongoing speculation about the so-called information paradox, the question of what happens to information that falls into a black hole. The extreme gravitational forces of a black hole warp spacetime in such a way that anything crossing its event horizon is lost to the universe. But does that information truly disappear? Could the study of gravitational shadowing around black holes reveal a way to recover this information? If so, it would revolutionize our understanding of both black holes and quantum mechanics, bridging a gap that has long been a topic of debate among scientists. Further complicating matters is the idea that there may be multiple types of black holes with different gravitational shadowing effects. While we often think of black holes in terms of stellar remnants, objects that form when massive stars collapse, there are other types of black holes that could play a more significant role in gravitational shadowing. For example, supermassive black holes, which exist at the centers of most galaxies, could create shadowing effects on a scale far beyond what we currently observe with stellar black holes. These supermassive black holes not only warp the fabric of spacetime around them but could also influence entire galaxy clusters, affecting the movement of stars, gas, and other cosmic materials. By studying the gravitational shadowing effects around these objects, we could gain new insights into the dynamics of galaxy formation and evolution. The role of gravitational shadowing in the broader context of cosmology and the structure of the universe is just as important. If gravitational shadowing can reveal hidden masses, unseen galaxies, and dark matter, it could help us map out the unseen parts of the universe. For instance, scientists are still trying to understand the distribution of dark matter in galaxy clusters. Dark matter doesn't emit light, making it invisible to traditional observational methods, but its gravitational effects can still be felt. The gravitational shadowing caused by dark matter-rich regions might allow us to detect these hidden masses, providing valuable clues about how dark matter behaves and interacts with ordinary matter. This could have major implications for the way we understand the formation of galaxies and the large-scale structure of the universe. Another fascinating idea in the study of gravitational shadowing is the potential connection between cosmic strings and these shadowing effects. Cosmic strings are hypothetical one-dimensional defects in spacetime that may have formed in the early universe. They are believed to be incredibly dense and could, in theory, cause large-scale gravitational effects. If cosmic strings exist, they could warp spacetime in a way that would create gravitational shadowing on a much grander scale than we currently observe with individual black holes or galaxy clusters. The study of these cosmic strings and their shadowing effects could provide new insights into the formation of the universe and the nature of the forces that shaped it. In many ways, cosmic strings could serve as a bridge between the realms of quantum mechanics and general relativity, offering a potential pathway toward the long-sought theory of quantum gravity. The role of gravitational shadowing could also become increasingly important as humanity ventures further into space. With missions planned to study the outer reaches of the solar system, send probes to distant stars, and eventually explore interstellar space, the need to understand gravitational phenomena on a cosmic scale will become more pressing. Understanding how light and matter interact in the presence of massive objects will be crucial for designing the next generation of space telescopes and observational instruments. These tools will allow us to observe distant stars and galaxies, detect exoplanets and far-off systems, and maybe even uncover new phenomena like gravitationally lensed objects or hidden stars. In addition to its application in space exploration, gravitational shadowing might offer practical implications for future technology here on Earth. One potential application could be in the field of GPS and satellite communications. As satellites orbit the Earth, their signals can sometimes be distorted by the gravitational fields of planets, moons, and other celestial objects. By understanding how gravitational shadowing works, we might be able to improve the accuracy and reliability of satellite-based systems, ensuring that signals are transmitted and received with greater precision. gravitational shadowing could also find applications in future efforts to detect new forms of energy. The study of massive cosmic objects, such as black holes, neutron stars, and even supernovae, could help us understand how extreme gravitational fields affect the energy around them. This might eventually lead to the discovery of new sources of energy, or new ways to harness the energy emitted by these powerful cosmic events. For instance, the study of gravitational waves, the ripples in space-time caused by the acceleration of massive objects, could lead to new technologies for detecting and manipulating energy on a cosmic scale. By tapping into these mysterious forces, we may unlock entirely new sources of power that could change the way we think about energy on Earth. As we continue to explore the implications of gravitational shadowing, we come to appreciate just how interconnected the universe is. Every massive object, every bend in spacetime, and every interaction between light and matter is part of a vast cosmic dance that we are only beginning to understand. Gravitational shadowing provides us with a unique perspective on this dance, offering a glimpse into the invisible forces that govern the universe's most fundamental processes. The study of gravitational shadowing is not just about understanding how light behaves in the presence of massive objects. It's about delving into the very fabric of space-time itself. It challenges our current models of physics, invites us to explore new dimensions of cosmic phenomena, and ultimately drives us closer to unlocking the deepest mysteries of the universe. Whether through the study of black holes, dark matter, exoplanets, or the fundamental forces that shape our reality, gravitational shadowing remains one of the most exciting frontiers in modern science. And as we continue to push the boundaries of our knowledge, we can only imagine what new discoveries await us just beyond the shadows. As we continue to probe the depths of gravitational shadowing, there are several fascinating pathways we have yet to explore. One of the most intriguing aspects of gravitational shadowing is how it connects to the theory of relativity, especially when considering Einstein's famous predictions about the warping of spacetime. For over a century, his general theory of relativity has provided the framework for understanding how gravity operates on large scales. Yet, when we delve into the microcosm of quantum mechanics, gravity becomes much harder to reconcile with the other fundamental forces. This discrepancy leads us to ask, can gravitational shadowing bridge this divide? In this quest to understand the quantum nature of gravity, gravitational shadowing may serve as an indirect test for theories such as string theory or loop quantum gravity. These are frameworks that attempt to merge quantum mechanics with general relativity, but they remain untested at the scale of real-world observations. However, with the precision of modern astronomical instruments, we might soon find ourselves in a position to make measurable predictions about how gravitational shadowing behaves in quantum systems. For instance, the subtle differences in shadowing effects around extremely dense objects, like black holes or neutron stars, could provide evidence of quantum gravitational phenomena. These effects may be too small for us to detect right now, but as technology improves, we could one day observe the quantum underpinnings of these massive cosmic events. As it stands, gravitational shadowing remains an essential tool for mapping the universe on the grandest scales. Observing how light bends around massive objects like black holes gives us crucial insights into the distribution of matter and energy in galaxies, clusters, and across vast cosmic voids. The bending of light caused by gravitational fields is known as gravitational lensing, and it provides us with a glimpse into areas of space where we would otherwise see nothing. This phenomenon is one of the most direct ways to observe distant objects, such as exoplanets, or even entirely hidden parts of our own galaxy, like the mysterious dark matter that makes up most of the universe's mass. Interestingly, gravitational lensing is not limited to just one type of lensing effect. In fact, gravitational shadowing opens up the possibility for a range of different lensing types, depending on the mass and shape of the object creating the gravitational field. We can observe strong gravitational lensing, where light is bent so dramatically that it forms arcs or rings around a massive object, and weak lensing, which produces more subtle distortions of background objects. The study of these phenomena has allowed astronomers to map out dark matter distribution and better understand the structure of galaxies and galaxy clusters. But even more astonishing is the potential for gravitational lensing and shadowing to reveal hidden, dark parts of the universe. The study of gravitational shadowing could lead to the discovery of unseen galaxies or the detection of exotic cosmic objects such as primordial black holes, tiny black holes that might have formed in the very early universe. These objects would be difficult to detect through conventional methods, but the way they bend light could provide clues to their existence. Such discoveries could dramatically alter our understanding of the universe's early stages and help us to reframe the questions we ask about cosmic evolution. If we uncover these hidden objects, it could provide us with insight into the universe's most enigmatic periods. The gravitational shadowing of supermassive black holes, which are thought to reside at the centers of most large galaxies, also presents another important research avenue. These objects are much more massive than stellar black holes, sometimes millions or even billions of times the mass of our Sun. Their enormous gravitational fields could create shadowing effects so pronounced that they influence the very structure of their host galaxies. Understanding how these supermassive black holes form and interact with their surroundings is critical to understanding galactic dynamics and evolution. Further expanding on the role of supermassive black holes in gravitational shadowing, we must consider their role in active galactic nuclei, AGNs. These regions, which contain supermassive black holes actively accreting matter, can emit extremely high levels of radiation. The accretion disks around these black holes could be responsible for some of the most energetic phenomena observed in the universe. The gravitational shadowing of these objects could provide a powerful tool to study how these systems evolve and how they impact their host galaxies. For example, the shadow cast by a supermassive black hole may reveal details about its accretion disk, its relativistic jets, and the distribution of matter in its vicinity. This, in turn, could help us understand how galaxies are affected by the massive black holes at their cores. Another captivating aspect of gravitational shadowing comes from its potential role in understanding cosmic time. Space-time itself is warped by gravitational fields, and these distortions can act as a natural time dilation mechanism. For instance, light traveling through a strong gravitational field will appear redshifted, meaning it will lose energy as it climbs out of the well of space-time. This effect, known as gravitational redshift, is a direct consequence of the warping of spacetime and provides critical information about the gravity fields of objects like black holes, neutron stars, and even large galaxy clusters. By measuring these gravitational redshifts in detail, scientists can uncover important information about the age of distant objects, the rate at which the universe is expanding, and the effects of gravitational forces on time itself. As we learn more about how time behaves in extreme gravitational fields, we could uncover fundamental truths about the nature of reality itself. Does time flow differently near black holes compared to the distant reaches of space? Can gravitational shadowing teach us more about the concept of time dilation, which has already been confirmed in experiments involving satellites orbiting the Earth? These questions may seem abstract now, but as we continue to measure gravitational shadowing, they may become more tangible, offering new insights into how the cosmos functions. The potential applications of gravitational shadowing extend well beyond theoretical physics and cosmology. In fact, there could be practical uses here on Earth. Gravitational wave detectors, like LIGO, Laser Interferometer Gravitational Wave Observatory, have already shown that we can measure the ripples in spacetime caused by massive objects colliding, such as black hole mergers. But what if we could use gravitational shadowing as a new kind of tool for measuring these events? The precise observation of gravitational shadowing effects could allow scientists to pinpoint the exact nature of the objects involved in these cosmic collisions. It could also open up new ways to detect gravitational waves indirectly, without relying solely on interferometry. Beyond gravitational wave detection, gravitational shadowing might help us better understand and develop advanced navigational techniques. As humanity ventures further into space, from landing on distant moons to exploring the outer planets, having a precise understanding of the gravitational fields that we encounter will be essential for navigation and maneuvering. In a future where humans may travel to other star systems, the principles of gravitational shadowing could help spacecraft avoid dangerous gravitational wells and harness the power of gravitational fields for propulsion or energy generation. As we continue to observe and measure the universe through the lens of gravitational shadowing, we may also discover phenomena that we never expected. The interplay between mass, space, and light is far from fully understood, and new discoveries could completely redefine our current models of physics. For example, we might uncover new types of objects that exert gravitational effects unlike anything we've seen before, or perhaps we will find that the fabric of spacetime is even more malleable than we had imagined. Moreover, the continued study of gravitational shadowing is opening the door to new possibilities in terms of technologies that could one day revolutionize fields like communication, energy generation, and even our understanding of consciousness. Could there be undiscovered forms of matter or energy hidden in the shadows of these immense gravitational fields? The answers may lie in exploring the invisible, in understanding how light and matter are affected by gravity, and in learning to interpret the subtle clues that gravitational shadowing offers us. The study of gravitational shadowing is far more than a technical pursuit. It's a profound journey into the very nature of the universe. Every discovery, every new observation, invites us to question the very foundations of physics and to consider the uncharted territories of space and time. The potential for breakthroughs is limitless, and as our ability to observe and interpret gravitational effects improves, so too will our understanding of the universe's most fundamental truths. Gravitational shadowing is not just a fascinating phenomenon, it is a key to unlocking the mysteries that have eluded scientists for centuries. Whether it's through the study of black holes, galaxy clusters, or dark matter, the shadows cast by gravity are leading us into a deeper, more profound understanding of the cosmos. As we continue to explore the implications of gravitational shadowing, we now enter a phase of analysis where even the smallest nuances could yield profound insights. As we delve deeper into this topic, we encounter increasingly complex interactions between matter, light, and space-time. At the heart of this discussion lies the concept of shadowing itself, and how it could transform our understanding of the most exotic phenomena in the universe. From dark matter to the very nature of black holes, gravitational shadowing may provide a key to answering questions that have baffled physicists for decades. In the context of dark matter, gravitational shadowing could serve as a crucial tool for indirect detection. Dark matter makes up roughly 27% of the universe's mass, but it does not emit, absorb, or reflect light, which makes it almost impossible to observe directly. However, by studying the gravitational effects that dark matter exerts on visible matter, we can begin to map its presence. Gravitational shadowing, particularly in the form of gravitational lensing, could give us the first concrete clues about the distribution of dark matter. When light from distant galaxies is bent by dark matter in galaxy clusters, it creates lensing effects that may hold the key to uncovering the hidden presence of this mysterious substance. The most profound implications of gravitational shadowing might arise from its role in understanding black holes, particularly the supermassive black holes that reside at the centers of most galaxies. Black holes are already enigmatic objects, whose very existence challenges our understanding of physics. Their gravitational influence is so intense that not even light can escape their grasp once it crosses the event horizon. Gravitational shadowing provides us with a unique window into the workings of these mysterious giants. One of the most exciting developments in recent years has been the Event Horizon Telescope's (EHT) capture of the shadow of a supermassive black hole in the galaxy M87. This groundbreaking image revealed a glowing ring of light surrounding a dark central region, the shadow of the black hole itself. It was the first direct visual evidence of a black hole's existence. However, the shadows cast by these supermassive black holes are more than just a photographic curiosity. They provide us with a window into the inner workings of the black hole's accretion disk, the region where matter is being drawn in and heated to extreme temperatures before being swallowed. By studying these shadows, we can gain deeper insights into the physics of accretion, the behavior of matter near the event horizon, and the fundamental properties of spacetime in these extreme environments. But even more fascinating than observing the shadows of supermassive black holes is the potential for studying the behavior of quantum fields in these regions. The intense gravitational fields near black holes could influence the way quantum particles interact with each other. In fact, some physicists have speculated that black holes might be a natural laboratory for studying quantum mechanics at scales that are otherwise inaccessible. The study of gravitational shadowing near these black holes could offer us a way to test quantum theories of gravity, which remain one of the greatest unresolved challenges in modern physics. Moreover, the study of gravitational shadowing opens up an entirely new realm for examining the dynamics of galaxy clusters. These massive structures, composed of galaxies bound together by gravity, are among the largest objects in the universe. The gravitational influence of these clusters is so immense that they bend light from objects located behind them, creating what we call strong gravitational lensing. This bending can form arcs, rings, or multiple images of distant galaxies. By carefully studying these lensing effects, we can map the distribution of mass within the cluster, including the mysterious dark matter that cannot be directly observed. Understanding the mass distribution in galaxy clusters is essential for understanding the formation and evolution of galaxies and clusters themselves. The study of gravitational shadowing also provides insight into the mysterious nature of space-time. Einstein's general theory of relativity predicted that massive objects should warp space-time around them, and this warping should be observable in the behavior of light. However, what we now understand as gravitational lensing and shadowing offers a much more detailed picture of how space-time behaves under extreme conditions. When light passes through regions of intense gravitational fields, the space-time it travels through is distorted, which can cause the light to bend, stretch, or even change color. By studying these effects in detail, we can begin to understand how space-time itself is affected by gravity at different scales, from the cosmic to the quantum. As we extend our exploration of gravitational shadowing to more exotic scenarios, such as near neutron stars, we encounter another fascinating possibility. Neutron stars, the remnants of massive stars that have exploded in supernovae, are incredibly dense objects that have extremely strong gravitational fields. These stars are often only a few kilometers in diameter, but they can contain more mass than the Sun. The gravitational fields around neutron stars are strong enough to warp spacetime to a significant degree, and the shadowing effects could provide us with valuable clues about their structure and behavior. Just like black holes, neutron stars are often surrounded by accretion disks that heat up and emit high-energy radiation. Observing how the light is bent around these stars could tell us more about the physical properties of the accretion disk and the star itself. The study of gravitational shadowing also intersects with the exploration of gravitational waves. Gravitational waves, ripples in spacetime caused by the acceleration of massive objects, are another key area of research in modern physics. Detectors like LIGO have already confirmed the existence of gravitational waves, which were first predicted by Einstein a century ago. But gravitational waves are not just limited to detecting the merging of black holes or neutron stars. They can also be influenced by gravitational shadowing effects. As gravitational waves pass through regions of space where gravitational fields are particularly strong, the waves themselves may be distorted. By studying these distortions, we can gain insights into the strength and structure of gravitational fields throughout the universe. In fact, some researchers believe that studying gravitational wave shadowing could provide a new way to test general relativity in extreme conditions. By examining how gravitational waves interact with various cosmic structures, we may uncover new phenomena that have yet to be predicted by existing models. The interplay between gravitational waves and gravitational shadowing could open the door to entirely new discoveries about how spacetime itself behaves under the influence of massive objects. At an even broader level, the exploration of gravitational shadowing could have profound implications for our understanding of the universe's overall structure. The way that light interacts with gravitational fields tells us a great deal about how matter is distributed across vast cosmic scales. For example, by observing gravitational lensing effects, we can map the distribution of galaxies and galaxy clusters, providing us with insights into the large-scale structure of the universe. Moreover, gravitational shadowing could offer a new tool for detecting unseen cosmic structures, such as rogue planets, black holes, or even entire galaxies that have yet to be observed. Through the lens of gravitational shadowing, we are not only uncovering the hidden aspects of the universe but also challenging the limits of our knowledge. As technology advances and our ability to observe these cosmic phenomena improves, we will continue to push the boundaries of what is possible. We are, quite literally, learning to see the unseen, examining the universe from angles and perspectives that were previously unimaginable. Gravitational shadowing is one of the most powerful tools at our disposal for unlocking the mysteries of the universe. Whether it's through observing the shadows of supermassive black holes, mapping the distribution of dark matter, or studying the extreme conditions near neutron stars, gravitational shadowing offers us a unique glimpse into the very fabric of space-time. As we continue to refine our observational techniques and push the frontiers of astrophysical research, we are poised to make discoveries that will reshape our understanding of the cosmos. The gravitational shadows cast by massive objects are not just scientific curiosities. They are the keys to unraveling some of the deepest mysteries of existence itself. Gravitational shadowing, as we've already discovered, extends beyond a mere observational curiosity. It serves as a window into the underlying mechanisms that shape the cosmos. As we continue to probe deeper into the intricacies of gravitational shadowing, it becomes increasingly apparent that its implications could reshape our understanding of the universe's formation and evolution. While the study of gravitational lensing has been a cornerstone in this field, its broader consequences, on the very fabric of reality itself, are only beginning to be explored. What we see, or what we don't see, may be far more revealing than we ever anticipated. One of the more intriguing aspects of gravitational shadowing is how it relates to the larger framework of cosmology. Understanding the structure of the universe on a grand scale hinges on our ability to observe distant objects and measure the light that reaches us. However, much of that light is influenced, sometimes dramatically, by the intervening gravitational fields of massive objects, galaxies, clusters, and even dark matter, between us and the light source. The bending of light due to these gravitational effects is not just an interesting optical phenomenon, but a crucial part of how we understand the mass distribution in the universe. In the context of galaxy formation and evolution, gravitational shadowing can reveal the invisible aspects of galaxies that are not immediately apparent in traditional optical surveys. For instance, the study of gravitational lensing effects can help map the dark matter halo of a galaxy, revealing the distribution of this elusive substance that makes up the majority of a galaxy's mass. This is vital for understanding how galaxies form and evolve over cosmic time scales. Without dark matter, the gravitational interactions that lead to galaxy formation simply wouldn't hold together, yet it has remained almost entirely invisible, detectable only through its gravitational effects. Gravitational shadowing provides us with a method to study dark matter in far greater detail than before, mapping its extent and role in galactic formation with precision. As we venture further into the more exotic territories of gravitational shadowing, we find that these phenomena also have direct applications in our quest for understanding the behavior of the very building blocks of space-time itself. One of the most exciting developments in recent decades is the potential to study quantum gravity through the influence of gravitational shadowing. At the interface between quantum mechanics and general relativity, a new theory of quantum gravity awaits discovery. Gravitational shadowing offers a method for observing and testing the effects of quantum field theory in curved space-time. The interaction between quantum fields and gravitational forces in regions of extreme gravity, like near black holes, neutron stars, or the event horizon of supermassive black holes, could offer us unprecedented access to understanding the quantum properties of gravity. If the shadow of a black hole can be studied in such detail that it reveals minute quantum fluctuations in spacetime, it could provide the first evidence for a theory of quantum gravity, combining the best aspects of quantum mechanics and general relativity. Through gravitational shadowing, we are not just observing shadows cast by massive objects. We are peering into the very fabric of space-time and probing the deepest mysteries of existence. Moreover, gravitational shadowing may even shed light on some of the most profound questions in theoretical physics. Take, for instance, the intriguing possibility of time dilation near black holes. As an object approaches the event horizon of a black hole, time appears to slow down relative to an observer at a safe distance. This warping of time, a consequence of the intense gravitational field, could have far-reaching implications for our understanding of time itself. The study of gravitational shadowing around black holes, especially those with active accretion disks, could provide vital data on how time behaves near the edge of spacetime, contributing to the larger body of knowledge on the nature of time and causality. But the relevance of gravitational shadowing isn't confined to the study of massive objects like black holes and galaxy clusters. In fact, even objects that are not typically considered massive enough to influence gravitational waves in significant ways could offer valuable insights. Rogue planets, for instance, are isolated planets that do not orbit a star but instead wander through the cosmos. These elusive objects could be detected through gravitational shadowing effects as their gravitational fields bend light from background stars. The discovery of rogue planets, those lone wanderers of the cosmos, could reshape our understanding of planetary formation and distribution, especially if gravitational shadowing allows us to detect their presence in ways we previously couldn't. The detection of rogue planets through gravitational lensing also opens up the intriguing possibility of identifying exoplanets in distant star systems. Gravitational shadowing could provide a new method for detecting planets that might otherwise remain invisible through traditional optical surveys. By studying how light is bent around stars and their surrounding planetary systems, astronomers could infer the presence of planets that are too far away or too faint to detect by conventional means. This could significantly expand the list of known exoplanets, contributing to a more detailed understanding of planetary systems across the galaxy and beyond. But what about the future of gravitational shadowing research? As technology advances, so too does our ability to observe and measure these effects with greater accuracy. The future promises even more sophisticated tools and techniques to probe gravitational shadowing in unprecedented ways. Instruments like the James Webb Space Telescope, JWST, with its powerful infrared imaging capabilities, will be able to observe distant galaxies, supernovae, and even the shadows of supermassive black holes with incredible clarity. The JWST could, for example, provide new insights into the formation of the first galaxies, revealing how they were shaped by dark matter and other unseen forces. Additionally, the development of next-generation gravitational wave detectors promises to offer even greater precision in studying the cosmic phenomena that produce these ripples in space-time. By observing how gravitational waves are influenced by gravitational shadowing, scientists could unlock new aspects of the nature of gravity, mass, and the behavior of space-time under extreme conditions. As these detectors improve, we could see the rise of a new era in which gravitational waves and shadowing effects are studied in tandem, providing a more complete picture of the universe's most mysterious objects. Beyond this, we may find ourselves in a position where the study of gravitational shadowing begins to inform other fields of physics. For instance, the study of high-energy particle physics could be influenced by our understanding of how gravity interacts with quantum fields in extreme environments. Similarly, gravitational shadowing could offer new perspectives on the study of cosmic rays and other high-energy particles, shedding light on the sources of some of the most energetic phenomena in the universe. As we explore the universe through the lens of gravitational shadowing, we are reminded of how much there still is to learn. With every shadow we observe, we uncover new layers of the universe, some of which may completely overturn our existing theories. The effects of gravity, once thought to be simple and predictable, reveal their full complexity when viewed through the lens of shadowing. In the years to come, gravitational shadowing could hold the answers to some of the most profound questions in science, questions that could shape our understanding of the cosmos for generations to come. As we continue to dive deeper into the realm of gravitational shadowing, it's important to address the broader implications of this phenomenon. The more we learn about how light behaves around massive objects, how it bends, warps, and distorts, the more we realize that this effect has the potential to revolutionize many of our core principles in physics. It's not just about understanding how massive objects influence light, but also about the fundamental relationship between matter, space, and time. Gravitational shadowing offers a glimpse into how the universe's building blocks interact, how mass warps the fabric of space-time, and how light, an essential carrier of information, can be altered by these forces. One of the most profound realizations brought on by the study of gravitational shadowing is its effect on our understanding of the universe's structure. In cosmology, the study of galaxy clusters, dark matter, and the large-scale structure of the universe has long relied on indirect measurements. Gravitational lensing, a direct consequence of gravitational shadowing, allows us to see how galaxies and galaxy clusters interact with light, offering a way to measure the distribution of mass across vast cosmic distances. This has opened a new window into understanding not just the visible matter we can observe, but the elusive dark matter that remains a mystery. To truly appreciate the implications of gravitational shadowing, it's helpful to explore its connection to one of the most baffling phenomena in the universe: dark energy. Dark energy, the mysterious force accelerating the expansion of the universe, could be connected to the gravitational effects we observe in lensing and shadowing. Some theorists suggest that the distortions we see in light from distant galaxies could be influenced by the effects of dark energy. This would mean that gravitational shadowing could provide new insights into the nature of dark energy, possibly revealing its influence on the large-scale structure of the universe in ways we never expected. The more we study these shadowing effects, the more we may uncover about the fundamental forces driving the cosmos. But gravitational shadowing is not merely confined to distant galaxies and theoretical physics. It has practical applications closer to home, in the way we observe our own galaxy. For instance, our understanding of the Milky Way has been dramatically enhanced by the study of gravitational lensing and shadowing effects. As light from distant stars and quasars passes through the galactic center, it bends around massive objects, such as supermassive black holes. These shadows allow scientists to measure the mass distribution within our galaxy with precision, shedding light on the complex dynamics at play in the heart of the Milky Way. This kind of observational data could be crucial for understanding the role of supermassive black holes in galaxy formation, and how galaxies evolve over time. Another intriguing application of gravitational shadowing is its potential to enhance our ability to detect exoplanets. We've discussed the power of gravitational lensing to reveal hidden planets and far-off star systems, but the phenomenon of shadowing could further refine our detection methods. Traditional techniques for finding exoplanets, such as the transit method and radial velocity measurements, rely on detecting the small, periodic changes in light caused by the presence of a planet. However, gravitational shadowing could provide a new, independent method for identifying exoplanets by observing how their gravitational influence bends light from background stars. This approach could lead to the discovery of planets that are too faint or too distant to be detected using traditional methods. As we push the boundaries of what we know, it's also important to consider the technological advancements that will enable us to explore gravitational shadowing in even more depth. The next generation of telescopes, such as the Extremely Large Telescope, ELT, being built by the European Southern Observatory, promises to revolutionize our ability to study distant galaxies and cosmic phenomena. These telescopes will have the resolution and sensitivity necessary to observe even the most subtle gravitational lensing effects, allowing us to map the distribution of mass across the universe with unprecedented detail. With these tools, we may finally be able to answer questions that have puzzled scientists for decades, such as the true nature of dark matter and dark energy, and how they shape the evolution of galaxies and the universe as a whole. In addition to ground-based telescopes, the development of space-based observatories could also play a key role in advancing our understanding of gravitational shadowing. Instruments like the James Webb Space Telescope, JWST, are equipped to observe the universe in infrared wavelengths, enabling them to see through the cosmic dust and gas that often obscure our view of distant galaxies. The JWST, with its ability to detect faint infrared signals from the early universe, could provide new insights into the early stages of galaxy formation and how gravitational shadowing might have influenced the distribution of matter in the young cosmos. The observations made by these space-based telescopes will likely lead to discoveries that will reshape our understanding of both the small-scale and large-scale structures of the universe. Equally fascinating is the role of gravitational shadowing in the study of black holes. Black holes, once thought to be purely theoretical, are now known to be a central feature in the evolution of galaxies. The study of their shadows, particularly the shadow cast by the supermassive black hole at the center of our galaxy, is providing new insights into their properties and behavior. Observing how light bends around these massive objects allows scientists to test predictions from Einstein's general theory of relativity and refine our understanding of how black holes interact with their surroundings. The Event Horizon Telescope, which produced the first ever image of a black hole's shadow in 2019, is just one example of the cutting-edge technology being used to probe the properties of these cosmic giants. As we continue to refine our observational techniques, it's likely that we will uncover even more surprises about the behavior of black holes, their role in shaping galaxies, and the very nature of space-time itself. The study of gravitational shadowing also connects to some of the most fundamental questions in theoretical physics. For instance, the observation of gravitational lensing and shadowing effects could provide crucial clues to understanding the nature of space-time and the quantum mechanics that govern its behavior. Some researchers believe that by studying the bending of light around black holes and other massive objects, we may be able to uncover evidence of quantum gravity, a field that seeks to merge the principles of quantum mechanics with the theory of general relativity. If we could understand how quantum effects operate in extreme gravitational fields, it might lead to a new, unified theory of the fundamental forces of nature. Gravitational shadowing, with its potential to reveal the subtle interactions between light and massive objects, could be one of the key tools in this quest for a deeper understanding of the universe. The road ahead in the study of gravitational shadowing is long, but the potential rewards are immense. We have only just begun to scratch the surface of what this phenomenon can teach us about the universe. From mapping the dark matter that governs the structure of galaxies, to shedding light on the nature of time and space itself, the study of gravitational shadowing holds the promise of unlocking some of the deepest mysteries of the cosmos. As our observational techniques improve, and as new technologies allow us to probe deeper into the heart of the universe, we may find that the gravitational shadows we observe are not just the result of bending light, but are instead windows into the very fabric of reality itself. As we continue exploring the implications of gravitational shadowing, it becomes increasingly clear that this phenomenon holds significant potential for revolutionizing our understanding of the universe. By observing how light behaves when it passes through gravitational fields, we are not just learning about the objects that cause these distortions, but also about the underlying structure of space-time itself. This process of light bending is far more than just a scientific curiosity. It is a powerful tool that offers insights into some of the most enigmatic aspects of the cosmos. One of the most profound revelations brought by gravitational shadowing is the impact it has on our understanding of the very nature of light and gravity. We know that light travels in straight lines in a vacuum, but when it encounters a massive object, its path bends. This bending, as described by Einstein's general theory of relativity, occurs because mass causes spacetime to curve, and light follows the curves of this warped spacetime. Gravitational lensing, which is a direct consequence of gravitational shadowing, reveals the existence of such massive objects like black holes, supermassive black holes, galaxy clusters, and even the elusive dark matter. These objects are often invisible to our traditional methods of observation, but through the manipulation of light, we are able to detect their presence. But what does this mean for our exploration of the universe? How does the study of gravitational shadowing push the boundaries of modern astronomy? To answer these questions, we must look at the way light travels through the universe and how it can be manipulated by large-scale structures. Gravitational lensing, for example, allows astronomers to peer into distant galaxies that would otherwise be hidden behind cosmic dust or vast distances. It acts like a cosmic magnifying glass, bending light to reveal galaxies billions of light-years away, sometimes even offering a glimpse into the universe as it was shortly after the Big Bang. This is not just a theoretical concept. Gravitational lensing has already enabled us to see the most distant and faintest galaxies, and in turn, it has enhanced our understanding of the formation and evolution of the universe. In addition to revealing distant galaxies, gravitational shadowing can also be used to study the large-scale structure of the universe. The distribution of mass in the universe is not uniform. Instead, matter tends to clump together in vast structures such as galaxy clusters and superclusters. By studying how light from more distant objects is bent as it passes through these structures, astronomers can map the distribution of matter in the universe. This has profound implications for understanding the role of dark matter, which makes up the majority of the mass in the universe but has so far eluded direct detection. Through gravitational lensing, we can study the influence of dark matter on the behavior of light, providing valuable clues about its existence and properties. The study of gravitational shadowing also touches on the very fabric of space-time itself. When we observe gravitational lensing around massive objects like black holes, we are witnessing a manifestation of how space-time curves under the influence of mass. These observations provide us with a unique opportunity to test the predictions of Einstein's general theory of relativity in extreme environments, where gravity is at its most intense. In particular, the region around the black hole, where space-time is warped to the extreme, offers an ideal setting for testing the limits of our understanding of physics. As we continue to refine our observational techniques and technology, it's likely that we will uncover more surprises about the behavior of light, mass, and gravity in these extreme environments. But the role of gravitational shadowing extends beyond theoretical implications. It also has practical applications that may shape the future of space exploration. The more we understand about how light behaves when it interacts with gravitational fields, the better equipped we will be to navigate the cosmos. For example, gravitational lensing can be used to pinpoint the locations of exoplanets. While traditional methods for detecting planets, like the transit method or radial velocity, rely on detecting the small shifts in light caused by a planet's presence, gravitational lensing provides a completely independent way to identify planets by observing how their gravity bends light from distant stars. This could lead to the discovery of new exoplanets, some of which may be located in the habitable zone of their parent stars, where conditions might be suitable for life. Another practical application of gravitational shadowing is in the study of cosmic events such as supernovae and gamma-ray bursts. By analyzing how the light from these events is bent by intervening masses, scientists can gain valuable information about the properties of the event itself and the objects in its vicinity. For instance, gravitational lensing can be used to study the shape and size of supernova remnants, providing a clearer picture of how these catastrophic events unfold and how they contribute to the formation of heavy elements. Similarly, the bending of light from distant gamma-ray bursts could provide insights into the mechanisms driving these powerful explosions, which are thought to be some of the most energetic events in the universe. In the search for a unified theory of physics, gravitational shadowing may also play a key role. One of the biggest challenges in modern physics is reconciling general relativity, which governs the behavior of large-scale objects like stars, planets, and galaxies, with quantum mechanics, which describes the behavior of particles at the smallest scales. Gravitational shadowing offers a unique opportunity to test the intersection of these two theories. By studying how light interacts with extreme gravitational fields, scientists may be able to uncover new clues about how quantum effects play a role in the fabric of space-time. This could be a crucial step toward developing a theory of quantum gravity, which seeks to combine the principles of quantum mechanics with general relativity. As we move forward into the next era of space exploration, the importance of understanding gravitational shadowing cannot be overstated. The more we learn about how light interacts with massive objects, the more we are able to explore the mysteries of the universe. With the advent of more powerful telescopes and advanced observational techniques, we are on the verge of a new era in astrophysics. The study of gravitational lensing and shadowing will undoubtedly play a pivotal role in this next chapter of discovery. In the future, it is likely that gravitational shadowing will not only enhance our understanding of the cosmos but also help us navigate new frontiers in space exploration. For example, the study of gravitational lensing could enable us to observe distant exoplanets, galaxy clusters, and even the earliest stages of the universe. It could also provide insights into the nature of dark matter and dark energy, two of the most perplexing and elusive substances in the universe. As our technology continues to improve and our understanding of gravitational shadowing deepens, it's clear that this phenomenon will be a key tool in our quest to unravel the secrets of the universe. Gravitational shadowing is more than just an interesting scientific curiosity. It is a powerful tool that has the potential to unlock some of the deepest mysteries of the cosmos. From revealing the presence of dark matter to offering insights into the behavior of black holes and the nature of spacetime, gravitational shadowing holds the key to understanding the universe at its most fundamental level. As we continue to explore this phenomenon, we can be certain that it will play a central role in shaping our understanding of the universe for years to come. As we continue to delve deeper into the phenomenon of gravitational shadowing, we find ourselves standing at the precipice of a new era in astrophysical discovery. The ability to observe and understand how light interacts with gravity has opened up previously unimaginable opportunities for exploration. It's as though we have just begun to scratch the surface of a vast, cosmic puzzle, with gravitational shadowing acting as a key to unlocking its many layers. But beyond the theoretical implications and practical applications we've already discussed, there are still many areas where gravitational shadowing holds the potential to revolutionize our understanding of the universe. One particularly intriguing avenue of research that is emerging is the relationship between gravitational shadowing and the study of gravitational waves. Gravitational waves are ripples in spacetime caused by the acceleration of massive objects, such as the merging of black holes or neutron stars. When these waves pass through the universe, they distort spacetime itself, much like a stone dropped into a pond creates ripples across the water's surface. While gravitational waves were first detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO, their study is still in its infancy. However, there is increasing interest in how gravitational lensing and shadowing might be used to enhance our understanding of these waves. Gravitational lensing can provide a new perspective on gravitational wave sources by allowing us to observe distant events that might otherwise be hidden behind massive cosmic structures. For example, when gravitational waves pass through regions of intense mass, such as galaxy clusters or black holes, they may produce subtle distortions in the waves that are detectable by advanced instruments. These distortions could provide valuable information about the nature of the event that caused the gravitational waves, allowing scientists to better understand the processes that generate these ripples in spacetime. In addition to their role in studying gravitational waves, gravitational shadowing effects could also help us probe some of the most extreme environments in the universe. Black holes, for example, are known to warp spacetime to an extreme degree, creating shadows that are visible to astronomers. These shadows, which occur when light from a background source is blocked by the black hole, provide crucial information about the size, shape, and structure of these enigmatic objects. The famous first-ever image of a black hole, captured by the Event Horizon Telescope in 2019, was a direct result of studying gravitational shadowing. The image showed the shadow of the supermassive black hole at the center of the galaxy M87, offering an unprecedented glimpse into the heart of one of the most mysterious objects in the universe. However, the black hole shadow is only one example of how gravitational shadowing can be used to study extreme cosmic phenomena. Gravitational lensing and shadowing can also be used to investigate other exotic objects, such as neutron stars, which are incredibly dense remnants of massive stars that have exploded in supernovae. Neutron stars have extremely strong gravitational fields, and their effects on light can be used to probe their internal structure. For example, by observing how light is bent as it passes near a neutron star, astronomers can learn more about the star's mass, rotation, and other physical properties. This ability to probe extreme environments is not limited to black holes and neutron stars. Gravitational shadowing is also crucial for studying the early universe, particularly the first few moments after the Big Bang. During this time, the universe was filled with hot, dense matter that was opaque to light. However, as the universe expanded and cooled, light was able to travel freely through space, and it is this light, specifically the cosmic microwave background radiation, that we detect today as a faint afterglow of the Big Bang. By studying how this light interacts with large-scale cosmic structures, including the remnants of the early universe's gravitational fields, astronomers can learn about the conditions that existed during the universe's infancy and gain insights into its evolution over time. The study of gravitational shadowing also has profound implications for cosmology, the study of the universe as a whole. As we continue to explore the effects of gravity on light, we can begin to map the distribution of matter in the universe with unprecedented precision. The study of galaxy clusters, for example, provides a detailed view of how matter is distributed on the largest scales. By observing how light from distant galaxies is bent as it passes through these massive structures, astronomers can create detailed maps of dark matter and other invisible components of the universe. These maps are crucial for understanding the large-scale structure of the universe, including the formation of galaxies, clusters, and superclusters, as well as the role of dark energy in the universe's accelerated expansion. As we look to the future of gravitational shadowing research, the potential for new discoveries seems limitless. The ongoing development of more advanced telescopes and observational techniques will allow us to observe gravitational lensing and shadowing with greater sensitivity and accuracy than ever before. This could lead to the discovery of entirely new classes of objects in the universe, such as dark stars or exotic forms of matter that have previously eluded detection. Furthermore, the combination of gravitational lensing with other observational techniques, such as X-ray and radio astronomy, could provide a more complete picture of the universe, allowing us to study objects and phenomena from multiple perspectives. One of the most exciting aspects of this research is the potential for gravitational shadowing to uncover the nature of dark matter and dark energy, two of the biggest mysteries in modern physics. While we cannot directly detect dark matter or dark energy, their presence can be inferred through their gravitational effects on visible matter. Gravitational lensing is one of the most powerful tools available for studying these invisible components of the universe. By carefully analyzing how light is bent as it passes through regions of the universe dominated by dark matter, scientists can begin to map the distribution of this mysterious substance. Similarly, gravitational shadowing can provide valuable clues about the nature of dark energy, which is thought to be responsible for the accelerated expansion of the universe. In the coming years, we can expect gravitational shadowing to continue playing a central role in our exploration of the cosmos. As our instruments become more sensitive and our understanding of gravitational lensing and shadowing deepens, we will be able to unlock new layers of the universe's secrets. From probing the earliest moments of the universe to mapping the distribution of dark matter and dark energy, gravitational shadowing will remain a vital tool in our quest to understand the fundamental forces that govern the cosmos. The phenomenon of gravitational shadowing is one of the most powerful and fascinating aspects of modern astrophysics. It provides a unique way to probe the nature of space-time, mass, and gravity, allowing us to explore some of the most extreme and distant regions of the universe. Whether it's observing distant galaxies, studying black holes and neutron stars, or uncovering the mysteries of dark matter and dark energy, gravitational shadowing continues to push the boundaries of our understanding. As we continue to refine our observational techniques and develop new technologies, it's clear that this phenomenon will remain a cornerstone of astrophysical research for years to come. Gravitational shadowing's influence stretches far beyond the technical realm of astrophysics. It shapes the very way we perceive the universe and challenge our fundamental understanding of the cosmos. As we continue to delve deeper into its mysteries, we uncover new potential applications, not only in our scientific quests but in everyday technological innovations. The nature of gravitational shadowing offers an intriguing reflection of how vast and interconnected the universe is. Just like a shadow, it hints at the presence of objects and forces that might otherwise go unnoticed, suggesting that there is so much more to discover in the deep expanse of space. One of the key areas in which gravitational shadowing could have profound applications is in the field of time travel. Though time travel is often relegated to the realm of science fiction, recent advancements in our understanding of space-time have rekindled speculation about its possibilities. The bending of space-time caused by gravitational fields can, in theory, create wormholes, tunnels through space-time that could, if they exist, provide shortcuts between distant parts of the universe. These theoretical constructs, often called Einstein-Rosen bridges, are essentially like cosmic tunnels, and they are thought to be deeply connected to gravitational effects like shadowing. In this context, gravitational shadowing could offer a unique window into wormholes or similar phenomena. By studying the bending of light around these theoretical passages, scientists may gain insights into their structure and properties, potentially opening the door to understanding how these shortcuts through spacetime could be used for time travel. While this remains purely speculative at this point, the implications of such discoveries are extraordinary, as they would not only redefine our understanding of the universe but also our place within it. Gravitational shadowing might, in the future, provide the critical evidence needed to confirm or disprove the existence of such time-altering phenomena. Beyond the theoretical, gravitational shadowing is also beginning to provide valuable insights into the search for extraterrestrial life. The search for habitable planets, known as exoplanets, has been one of the most exciting and rapidly advancing fields in astronomy over the past few decades. While many exoplanets have been detected through traditional methods, like the transit method or radial velocity, gravitational shadowing offers a unique and complementary approach. The bending of light caused by a planet's gravity can alter the light coming from stars, providing new methods for detecting exoplanets that might otherwise remain hidden. Additionally, gravitational shadowing could also help us detect exoplanets in extreme environments, such as those in the habitable zone of black holes or those that exist in the chaotic heart of galaxy clusters. These environments are often hostile and difficult to study, but gravitational lensing could give us the tools to observe the subtle effects of planets and stars that are hidden behind more massive objects. These observations would provide critical information about the conditions of these distant worlds, potentially revealing signs of life in the most unlikely places. While we are still far from answering the age-old question of whether we are alone in the universe, gravitational shadowing is offering us a new lens through which to explore this possibility. As we continue our exploration of the effects of gravity on light and matter, the field of gravitational shadowing promises to grow in importance, yielding not only groundbreaking scientific discoveries but also technologies that could have wide-ranging impacts. One such potential application is in the development of advanced space telescopes and observational tools. The very principles of gravitational shadowing could inspire new methods of collecting data from distant parts of the universe, using natural phenomena like gravitational lensing to magnify and clarify distant cosmic objects. These advanced telescopes could allow us to peer deeper into the universe's past, observing phenomena that occurred billions of years ago, potentially revealing answers to some of the biggest questions in science. For example, we might be able to observe the formation of the first galaxies, stars, and even the earliest moments of the universe itself, providing a clearer picture of how our cosmos evolved over time. Additionally, new technologies inspired by gravitational shadowing could also improve our ability to observe dark matter and dark energy, two of the most enigmatic components of the universe. While we currently have limited ways of detecting these substances directly, their influence on light and gravity could allow us to map their distribution across the cosmos with increasing precision. One of the most compelling future applications of gravitational shadowing might come in the form of space navigation and travel. Just as we use the Earth's gravitational field to assist in satellite launches and spacecraft trajectories, future space travelers could potentially harness the power of gravitational shadowing to navigate through space more efficiently. By understanding how gravitational fields bend light and other forms of radiation, we could develop methods to slingshot spacecraft around massive objects, accelerating them toward distant destinations without the need for additional fuel. This technique, known as gravitational assist, is already used in missions like NASA's Voyager, but the advanced understanding of gravitational shadowing could significantly improve the precision and efficiency of these maneuvers. In parallel, gravitational shadowing may also play a critical role in studying the interstellar medium, the vast, largely unexplored space between stars. This region, filled with gas, dust, and cosmic rays, often contains structures and phenomena that are difficult to study because they are so diffuse and remote. However, by studying how light is bent and shadowed by objects within the interstellar medium, we could gain important insights into the nature of this space. For example, we might be able to map the distribution of cosmic dust and gas, better understanding how stars and galaxies form and evolve. This, in turn, could offer new perspectives on the processes that govern the larger structure of the universe, from star birth to the formation of galaxy clusters. In many ways, gravitational shadowing is a prime example of how the smallest, most subtle effects can provide the most profound insights into the nature of the cosmos. What began as a purely theoretical concept, formulated by Einstein over a century ago, has now become an essential tool in our astronomical toolbox. Whether it's through revealing the nature of black holes, helping us detect exoplanets, or potentially even enabling new forms of space travel, gravitational shadowing has already reshaped our understanding of the universe and will continue to do so for generations to come. The ultimate question we must ask is this: what new frontiers will gravitational shadowing help us discover in the coming years? The vastness of space is constantly expanding, and as our instruments improve and our understanding of the fundamental forces deepens, we may soon be able to answer some of the most profound questions that have ever been asked. What is the true nature of dark matter and dark energy? Can we unlock the secrets of time travel? How many more secrets of the universe lie hidden in the shadows? Only time will tell. But one thing is certain: gravitational shadowing will continue to be a guiding force, illuminating the deepest corners of the universe and providing us with the tools we need to explore its most distant reaches. As we move further into the exploration of gravitational shadowing, we must acknowledge the fascinating potential that lies in the unknown. While many theories and concepts have already been proposed, the future of research in this area is full of promise and uncertainty. Scientists and researchers around the world are constantly innovating, looking for new ways to observe, measure, and utilize the effects of gravity and its influence on light, matter, and spacetime itself. The impact of gravitational shadowing stretches across multiple disciplines, from astronomy and cosmology to practical applications in technology, transportation, and beyond. One of the most exciting aspects of gravitational shadowing is the potential for unlocking more information about the earliest moments of the universe. The concept of the cosmic microwave background radiation is a key part of the evidence supporting the Big Bang theory, and gravitational shadowing could offer additional layers of detail about the origin of our universe. Scientists are already using gravitational lensing to study distant galaxies and other cosmic structures that formed shortly after the Big Bang, but there's still much more to learn. Gravitational shadowing, especially in combination with advanced telescope technology, could help us study the distribution of matter and energy in the earliest stages of the universe's evolution, providing critical clues about how the universe expanded and evolved into its current state. For example, gravitational shadowing could be used to observe the formation of supermassive black holes. These massive objects are thought to exist at the centers of most galaxies, including our own Milky Way, and they are believed to have formed early in the universe's history. Gravitational lensing effects could offer us a new perspective on how these supermassive black holes came to be, by revealing their interactions with surrounding matter and light. By observing how light bends and distorts as it passes near these black holes, we could gain insights into their growth and the role they played in shaping the galaxies around them. In addition to studying distant phenomena, gravitational shadowing could have direct applications in studying the structure of our own galaxy. The Milky Way is filled with mysterious objects, from stellar remnants and nebulae to dark matter and black holes. These objects interact with light in ways that can be difficult to observe using traditional methods, but gravitational shadowing could provide a way to see them by analyzing how they distort the light from distant stars or galaxies. By observing how light bends as it passes near these objects, we could gather important data on their size, location, and composition. One particularly intriguing possibility is that gravitational shadowing could help us map the distribution of dark matter in the universe. While scientists know that dark matter exists, its exact nature remains elusive. Gravitational effects are the only way we currently know to detect dark matter, as it does not emit light or other forms of radiation. By studying the way gravitational shadowing bends light around clusters of galaxies, we can infer the presence of dark matter and begin to understand its role in the formation of the cosmos. In the future, this could lead to breakthroughs in our understanding of dark matter's composition and its interactions with ordinary matter. Another fascinating aspect of gravitational shadowing lies in the possibility of observing the so-called gravitational wave phenomena. Gravitational waves are ripples in spacetime caused by the acceleration of massive objects, such as the collision of black holes or the explosion of supernovae. These waves were first predicted by Albert Einstein in his theory of general relativity, and were finally detected by the Laser Interferometer Gravitational Wave Observatory, LIGO, in 2015. The study of gravitational waves has since become one of the most exciting fields in astrophysics, allowing scientists to detect and study previously invisible phenomena. Gravitational shadowing could enhance the study of gravitational waves by providing a way to observe their effects on light and matter. As gravitational waves travel through space, they distort the fabric of space-time itself, causing temporary ripples that can affect the path of light. By studying how light behaves in the presence of gravitational waves, researchers could gain valuable insights into the properties of these waves, their sources, and how they propagate across the universe. This could open up new ways to study extreme astrophysical events, such as black hole mergers and neutron-star collisions, in greater detail. In addition to its scientific applications, gravitational shadowing could have practical implications for the future of space exploration. One potential application of gravitational shadowing in space travel is in the concept of gravitational slingshot maneuvers, which are already used by spacecraft to gain speed and alter their trajectories. In these maneuvers, a spacecraft flies close to a planet or other massive object, using its gravitational field to accelerate and change direction. This technique has been successfully employed in missions like NASA's Voyager, but by studying gravitational shadowing effects more deeply, scientists may discover new ways to optimize these maneuvers, enabling faster and more efficient travel through the cosmos. Furthermore, gravitational shadowing could also inspire new forms of propulsion systems. As we explore the possibility of interstellar travel, we may find that harnessing the power of gravitational fields could provide a novel way to accelerate spacecraft without the need for traditional rocket engines. This could dramatically reduce the amount of fuel required for long-duration space missions and make the prospect of traveling to distant stars more feasible. Such advancements could take us one step closer to exploring the farthest reaches of the universe and even colonizing other planets. In the more immediate future, gravitational shadowing could also have an impact on satellite technology and space communications. As more and more satellites are launched into orbit around Earth and beyond, the need for efficient communication systems will become increasingly important. By studying how gravitational fields influence the transmission of signals, scientists could develop new ways to improve satellite communication, ensuring that messages can travel long distances with minimal interference. Gravitational shadowing's influence also extends to our understanding of fundamental physics. The study of how light interacts with gravitational fields provides a natural laboratory for testing theories of gravity and spacetime. By observing how gravitational lensing affects light from distant stars or galaxies, scientists can test Einstein's theory of general relativity in extreme conditions, such as near black holes or in the presence of dark matter. This kind of research could lead to new insights into the nature of gravity, spacetime, and the fundamental forces that govern the universe. It may even reveal new aspects of quantum mechanics, shedding light on the long-standing mysteries of the quantum world and its relationship with gravity. Despite all the advancements made so far, there is still so much we don't know about gravitational shadowing. As we continue to push the boundaries of technology and research, it's likely that new discoveries will emerge, unlocking even more of the universe's secrets. Gravitational shadowing has already proven itself to be a powerful tool in the field of astrophysics, but its true potential may still be waiting to be fully realized. Whether it's through uncovering the mysteries of dark matter, enabling faster space travel, or providing new ways to observe distant galaxies, the possibilities are endless. As we stand on the threshold of this exciting frontier, one thing is clear: gravitational shadowing will continue to be a critical component in our quest to understand the universe. Whether it's bending light around massive objects or revealing hidden structures within the fabric of spacetime, the effects of gravity's shadow have far-reaching implications. The more we study these phenomena, the more we will uncover about the nature of the cosmos and our place within it. Gravitational shadowing, as we have seen, is not just a phenomenon that influences the behavior of light but is deeply intertwined with our understanding of the universe's structure and evolution. It is an essential component in many ongoing and future scientific endeavors, from cosmological research to space exploration. The broader implications of gravitational shadowing are vast, and as our technologies and methodologies improve, we will continue to uncover layers of the universe's mysteries that were once thought to be out of reach. One area where gravitational shadowing could revolutionize our understanding is in the study of galaxy formation and evolution. Galaxies are complex systems of stars, gas, dust, and dark matter, and their formation is still a topic of intense research. By studying how gravitational shadowing influences the light from distant galaxies, we can learn more about their structure, dynamics, and the forces at play in their formation. For instance, gravitational lensing could reveal the presence of massive unseen objects in the cores of galaxies that might otherwise be hidden. These objects could play a critical role in the formation and evolution of galaxies, acting as catalysts for star formation or influencing the distribution of dark matter. The study of gravitational shadowing could also have a profound impact on our understanding of the so-called missing mass in the universe. Despite the fact that the universe seems to contain far more matter than we can see directly, much of this matter is invisible. This dark matter is theorized to account for the vast majority of the universe's mass, but its exact nature remains elusive. Gravitational shadowing offers one of the few ways we can detect and study dark matter. By observing the way light bends around galaxy clusters, we can map out the distribution of dark matter, which doesn't emit or interact with light. This technique has already provided valuable insights into the large-scale structure of the universe, but it could reveal even more about the properties and behavior of dark matter, potentially leading to breakthroughs in our understanding of one of the universe's most fundamental mysteries. Moreover, gravitational shadowing might help address another key challenge in modern cosmology: the problem of the universe's expansion. One of the most important discoveries of the 20th century was the observation that the universe is expanding at an accelerating rate. This discovery, made in the late 1990s, has led to the development of theories involving dark energy, a mysterious force thought to be driving the acceleration. However, the nature of dark energy is still not well understood, and it remains one of the most perplexing aspects of modern physics. Gravitational shadowing may offer a new way to study the effects of dark energy. By analyzing how light from distant galaxies is bent and distorted by massive structures in the universe, scientists can map the growth of cosmic structures over time. This, in turn, could reveal more about how the universe is expanding and whether dark energy is the cause of this acceleration. It could also shed light on whether dark energy behaves uniformly across space and time, or whether its effects vary depending on the scale of the universe being studied. In the realm of theoretical physics, gravitational shadowing could lead to new insights into the nature of spacetime itself. General relativity, Einstein's theory of gravity, describes how massive objects curve the fabric of spacetime, causing the observed effects of gravity. Gravitational lensing and shadowing provide a unique opportunity to test these predictions in extreme environments. For example, near the event horizon of a black hole, spacetime is severely warped, and the behavior of light becomes radically different. By studying how light behaves in such environments, scientists can test the limits of general relativity and explore whether it holds up in these extreme conditions or whether new physics is needed. Additionally, gravitational shadowing could help refine our understanding of quantum gravity. Quantum mechanics, the theory that governs the behavior of subatomic particles, and general relativity, which describes the behavior of large-scale cosmic structures, have long been at odds. A unified theory of quantum gravity remains one of the greatest challenges in physics, as it would need to reconcile the principles of both of these theories. Gravitational shadowing, by providing data on the behavior of light and matter in extreme gravitational fields, could offer valuable clues about how quantum effects interact with the curvature of spacetime. Such insights could pave the way for a deeper understanding of the fundamental nature of the universe and lead to the development of a theory of quantum gravity. One of the more speculative, yet exciting, possibilities that arises from gravitational shadowing is the potential for future technology. Imagine, for instance, using gravitational shadowing effects for communication or even energy generation. While this may sound like science fiction today, the concept of manipulating gravitational fields for practical use has been explored in theoretical physics. In the distant future, we might be able to harness gravitational effects, including shadowing, to develop new technologies that could revolutionize space travel, communication, and energy systems. The possibility of using gravitational fields as a means of propulsion or energy storage could open up new frontiers in space exploration, making interstellar travel more feasible and efficient. Another potential application lies in the area of space-time research. By understanding how light behaves in different gravitational environments, scientists could better map out the fabric of space-time itself. This could lead to breakthroughs in how we understand the flow of time and its relationship to gravity. The ultimate goal might be to develop technologies that allow us to manipulate space-time, or even potentially to control the speed at which time passes under certain conditions. While this idea remains firmly in the realm of theoretical physics, the study of gravitational shadowing could provide a stepping stone toward more profound advancements in our understanding of time and space. As we move into the next phases of gravitational research, one thing is clear: this field is full of potential. Gravitational shadowing effects, once considered a curiosity of astrophysical phenomena, have now become an essential tool for probing the deepest mysteries of the cosmos. They provide us with a window into the unseen aspects of the universe, from dark matter and black holes to the very fabric of spacetime itself. The implications for science, technology, and our understanding of the universe are far-reaching, and we have only begun to scratch the surface of what can be achieved. As we continue exploring gravitational shadowing, it becomes evident that this phenomenon is not only crucial for understanding the cosmos, but also for future advancements in technology and scientific discovery. The ability to study how light interacts with gravitational fields opens up new possibilities in astrophysics and even fundamental physics, providing deeper insights into the nature of the universe. As our understanding of gravitational lensing and shadowing grows, we can expect even more breakthroughs, some of which could reshape how we view our place in the universe. One of the most exciting prospects in this area is the potential to use gravitational shadowing as a tool for exploring exotic astrophysical objects. Black holes, in particular, remain one of the most fascinating and enigmatic objects in space. While we have made significant strides in observing black holes, particularly with the advent of technologies like the Event Horizon Telescope, the role of gravitational shadowing in black hole studies cannot be overstated. Gravitational shadowing provides a unique way to detect and study the extreme environments around black holes. The shadow cast by a black hole, essentially the region where light can no longer escape due to the immense gravitational pull, gives us a direct look at the properties of these objects. By studying these shadows, scientists can learn more about the size, shape, and behavior of black holes, as well as gain insight into the effects of gravity near the event horizon. The concept of gravitational microlensing is another area where shadowing could yield important discoveries. Microlensing occurs when a small, compact object, such as a star or a planet, passes in front of a more distant background object. The gravitational field of the foreground object bends and amplifies the light from the background object, creating a temporary lens effect. This effect can be used to detect objects that would otherwise be invisible, such as exoplanets or rogue planets, planets that do not orbit a star but instead drift through space. Gravitational microlensing has already been used in several high-profile surveys, such as the Macho and OGLE projects, to detect dark matter and exoplanets. The more we refine our ability to detect and analyze microlensing events, the better we will understand the distribution of matter in the universe, including dark matter, and the frequency and diversity of planetary systems across the galaxy. Another intriguing aspect of gravitational shadowing is its potential role in understanding the expansion of the universe. As mentioned earlier, the acceleration of the universe's expansion is one of the most profound discoveries of modern cosmology. This acceleration, attributed to the mysterious dark energy, has left scientists with many questions that remain largely unanswered. Gravitational shadowing could help answer some of these questions by allowing us to observe the impact of dark energy on the large-scale structure of the universe. By studying how gravitational lenses distort the light from distant galaxies, we can track the growth of cosmic structures over time. This could provide critical data on the rate of expansion and the role dark energy plays in shaping the cosmos. Gravitational shadowing might also give us insights into the early universe and how the expansion evolved shortly after the Big Bang, helping to refine our models of cosmic inflation and the formation of galaxies and other structures. The role of gravitational shadowing in observing dark matter is particularly noteworthy. As we've seen, dark matter is one of the most significant components of the universe's total mass, yet it cannot be observed directly. It does not emit, absorb, or reflect light, which makes it invisible to traditional observation methods. However, its presence is inferred through its gravitational effects on visible matter, such as stars and galaxies. Gravitational lensing, especially when combined with other observational techniques, is a powerful tool for mapping the distribution of dark matter. By observing how light is bent around galaxy clusters, scientists can detect the invisible mass that warps space-time. These observations help to create detailed maps of dark matter, shedding light on its distribution across the universe and offering clues to its properties. Understanding dark matter is a crucial step towards solving one of the greatest mysteries in modern physics, and could lead to a deeper understanding of the universe's structure and evolution. Beyond the realm of astrophysics, gravitational shadowing could have more practical applications in the future. While this might seem far off, the potential for gravitational effects to be harnessed for technology is an intriguing possibility. For instance, in the field of communication, researchers are exploring how gravitational waves and even gravitational lensing might be used to enhance signals, particularly in the context of long-distance space communication. The bending of light in gravitational fields could allow for more efficient transmission of signals, even over vast cosmic distances. While this concept remains speculative, the continued study of gravitational shadowing could reveal new ways to leverage the fundamental forces of nature for practical use. Another area where gravitational shadowing could have practical applications is in space travel. Understanding the gravitational fields of distant objects could help space agencies plan more efficient space missions. By using gravitational shadowing to detect the mass and density of celestial bodies, we could refine our models of gravitational assists and optimize trajectories for interplanetary travel. This would be particularly useful for long-term space exploration missions, such as those aimed at reaching the outer planets, or even interstellar space. Gravitational shadowing could help identify regions of space where gravitational anomalies exist, allowing spacecraft to take advantage of these anomalies for propulsion, potentially reducing fuel requirements and travel time. The broader implications of gravitational shadowing also extend to the philosophical realm. The study of gravitational effects challenges our understanding of the universe and our place within it. As we explore these fundamental forces and their influence on the cosmos, we begin to confront some of the most profound questions about existence, space, and time. How did the universe come to be in its current state? What are the underlying principles that govern its behavior? Can we ever fully comprehend the nature of space-time, or will we always be limited by the confines of our current understanding? The study of gravitational shadowing represents a frontier of science that combines the deep mysteries of the cosmos with the promise of new discoveries. It is a field that stretches the boundaries of our imagination, challenging us to think beyond the familiar and consider the universe in ways that were once unimaginable. As we continue to probe the dark corners of space, gravitational shadowing will undoubtedly remain a crucial tool in our quest to understand the true nature of the universe. As we move forward, the potential applications of gravitational shadowing continue to grow. More sophisticated instruments are being developed to observe and measure the effects of gravitational fields with greater precision, and these advancements could lead to even deeper insights into the universe's fundamental structure. With the ongoing improvements in technologies like the Event Horizon Telescope, which captured the first image of a black hole's event horizon, we are now in a position to study the nuances of gravitational shadowing with an unprecedented level of detail. These advancements promise to unlock secrets not just about the nature of black holes, but about the very fabric of spacetime itself. The study of gravitational shadowing could also help address one of the most intriguing and paradoxical aspects of modern physics: the unification of general relativity and quantum mechanics. These two pillars of modern physics have long been at odds, with general relativity describing the behavior of massive objects in spacetime and quantum mechanics explaining the behavior of subatomic particles. While both have been confirmed through experiments and observations, they remain incompatible at their core. Gravitational shadowing, particularly in extreme environments like the vicinity of black holes, could offer a unique opportunity to explore this conflict. By studying how light and matter interact with extreme gravitational fields, scientists may gain insights into how the two theories can be reconciled. Some physicists believe that phenomena like gravitational shadowing might reveal new ways to think about gravity on a quantum level, possibly leading to a theory of quantum gravity that could unite these two disparate frameworks. In addition to theoretical implications, gravitational shadowing could also have profound effects on our understanding of the universe's past and future. By observing distant galaxies and galaxy clusters through the lens of gravitational effects, we can study the evolution of cosmic structures over billions of years. Gravitational lensing allows astronomers to look back in time, seeing light that has traveled across vast distances and been bent by massive cosmic structures. This process could help answer some of the most fundamental questions in cosmology. How did galaxies form? What were the conditions in the early universe? How did dark matter influence the development of large-scale cosmic structures? These are questions that could shape our understanding of the universe's origin and evolution for decades to come. But the most exciting aspect of gravitational shadowing may lie in its potential to reveal entirely new phenomena, effects and objects that we can't yet even predict. As our understanding of the universe deepens, we may find that gravitational shadowing is not just a tool for studying familiar objects like black holes or galaxy clusters, but a window into entirely new realms of astrophysics. For instance, could gravitational lensing uncover new types of cosmic entities, ones that are hidden from direct observation? What if there are entirely new forms of matter or energy that we are not yet aware of, but that can be detected through their gravitational interactions? The possibilities are endless, and the mysteries only multiply as our observational tools become more advanced. One fascinating possibility that arises from gravitational shadowing is the detection of strange and exotic phenomena beyond our current understanding. Could we one day use gravitational shadowing to detect alien megastructures, massive artificial constructions built by advanced civilizations? The idea may sound speculative, but it's not beyond the realm of possibility. If a sufficiently large structure, such as a Dyson sphere or an enormous space station, existed around a star, it could potentially cast a gravitational shadow that would be detectable using modern gravitational lensing techniques. The study of these kinds of phenomena could open up a new frontier in the search for extraterrestrial intelligence, offering us the chance to detect evidence of civilizations far beyond our own. While we are still far from proving such ideas, the continued study of gravitational shadowing could ultimately lead us to groundbreaking discoveries in this area. Another area that holds promise is the study of gravitational waves, ripples in spacetime caused by massive objects accelerating through the universe. These waves were first predicted by Albert Einstein in 1915 as part of his theory of general relativity, but it wasn't until 2015 that scientists detected gravitational waves for the first time, thanks to the Laser Interferometer Gravitational Wave Observatory, LIGO. These waves can be used to study events that are invisible to traditional telescopes, such as the collision of black holes or neutron stars. Gravitational waves carry information about the nature of the objects that created them, and their study offers a unique window into some of the most violent and energetic events in the universe. In the future, gravitational shadowing could help enhance our understanding of gravitational waves by providing additional context for the events that generate them, helping scientists refine their models of these cosmic disturbances. The prospect of combining gravitational shadowing with other observational techniques, such as radio waves, X-rays, and gamma rays, also presents an exciting avenue for future research. By observing astronomical objects across multiple wavelengths, scientists can build a more complete picture of the forces at play. For example, using gravitational lensing in combination with X-ray observations of a distant galaxy cluster could provide valuable information about the mass distribution within the cluster and how it affects the surrounding spacetime. This approach would allow for a more detailed study of the complex interactions between matter and gravity in the universe, helping to unlock new insights into the nature of space, time, and energy. Ultimately, the study of gravitational shadowing represents a convergence of multiple branches of astrophysics, offering a unique opportunity to explore the universe from a fresh perspective. Whether it's revealing the mysteries of black holes, providing insight into the structure of dark matter, or helping us unlock the secrets of the universe's earliest moments, gravitational shadowing holds the key to many of the most important questions in science. And as our technological capabilities continue to improve, it's likely that we'll uncover even more surprises along the way. The universe is full of hidden wonders, and gravitational shadowing is one of the tools that will help us uncover them. So, what does the future hold? Perhaps we are on the brink of a new era in astrophysical research, one where the study of gravitational shadowing leads to groundbreaking discoveries that redefine our understanding of the cosmos. As we continue to push the boundaries of our knowledge, we may find that the universe is even stranger and more wondrous than we could have ever imagined. The mysteries of gravity, light, and the very fabric of spacetime await us, and with each new discovery, we come one step closer to unlocking the secrets of the universe itself. As we continue to explore the depths of gravitational shadowing, we must recognize that the pursuit of knowledge in this area is still in its early stages. The universe is vast, and we are only beginning to scratch the surface of its complexities. One of the most fascinating aspects of gravitational shadowing is its potential to reveal phenomena that we cannot yet even conceptualize. Just as the discovery of gravitational waves in 2015 opened up a new realm of astrophysical research, gravitational shadowing could one day lead us to uncover even more surprising and unimaginable phenomena. In the context of black holes, gravitational shadowing is already yielding profound insights. The famous image of the supermassive black hole at the center of the galaxy M87, captured by the Event Horizon Telescope in 2019, was a watershed moment in our understanding of black holes. That image provided direct evidence of the existence of event horizons and demonstrated the ways in which light and matter interact with extreme gravitational fields. However, the event horizon itself, the boundary beyond which not even light can escape, remains elusive, and the deeper properties of black holes continue to be a mystery. Gravitational shadowing offers a unique tool for studying the behavior of matter and energy near the event horizon, shedding light on some of the most enigmatic and extreme environments in the universe. As astronomers develop more advanced instruments to detect gravitational waves and measure gravitational lensing with greater precision, we can expect even more breakthroughs in this field. One particularly exciting development is the upcoming launch of the James Webb Space Telescope, which is set to provide unprecedented views of distant galaxies and the objects within them. This next-generation telescope will allow scientists to study the cosmic phenomena that create gravitational shadows in much more detail than ever before. The Webb telescope's advanced infrared capabilities will enable it to peer through the dust and gas that often obscure our view of distant objects, allowing for clearer observations of galaxies, black holes, and other extreme objects that create gravitational shadows. But it's not just the technology that is evolving. Our theoretical understanding of gravitational shadowing is also advancing. The equations that govern the bending of light in a gravitational field are becoming more refined, and the simulation models used to predict the behavior of light and matter in the presence of massive objects are becoming increasingly sophisticated. These models are crucial for interpreting the data we collect through gravitational lensing and shadowing effects. By improving our understanding of these phenomena, scientists can better predict where to look for interesting gravitational shadows and how to interpret the data once it's collected. One intriguing area of research involves the study of gravitational shadowing in the context of galaxy clusters. These enormous structures, which contain hundreds or even thousands of galaxies, are often surrounded by vast clouds of dark matter and hot gas. The gravitational influence of the cluster can distort the light from background galaxies, creating gravitational lenses that allow scientists to map the distribution of mass within the cluster. By studying these gravitational shadows, researchers can learn more about the nature of dark matter and the role it plays in shaping the large-scale structure of the universe. Dark matter remains one of the greatest mysteries in astrophysics, and gravitational shadowing could be the key to unlocking its secrets. The study of gravitational shadowing could also offer insights into the nature of time and space itself. One of the most profound implications of Einstein's theory of general relativity is the idea that gravity can bend the very fabric of space-time. The bending of light around massive objects, such as black holes or galaxy clusters, is a direct result of this curvature. Gravitational shadowing provides a powerful tool for observing the effects of this curvature, offering a glimpse into the deeper workings of space-time. By analyzing how light bends and distorts around massive objects, scientists can test and refine our understanding of the fundamental nature of space and time. Could gravitational shadowing eventually lead to new insights into the structure of the cosmos itself? Perhaps, as we push the limits of our observational tools, we will discover that space-time is even more malleable and dynamic than we currently understand. Another potential avenue for future research is the study of gravitational shadowing in more exotic environments, such as the vicinity of neutron stars and white dwarfs. These objects, like black holes, have incredibly strong gravitational fields, but unlike black holes, they do not have event horizons. Neutron stars, for example, are the remnants of massive stars that have undergone supernova explosions. They are incredibly dense, with masses greater than that of the Sun compressed into a sphere only a few kilometers in diameter. The intense gravitational fields of neutron stars can bend light in ways that are similar to black holes, and gravitational shadowing could provide valuable insights into the properties of these exotic objects. Similarly, white dwarfs, which are the remnants of stars that were once similar to our Sun, also produce gravitational fields strong enough to cause gravitational lensing effects. While they are not as extreme as neutron stars or black holes, they still offer a fascinating area of study for gravitational shadowing. By observing how light from background stars is bent as it passes near a white dwarf, scientists could learn more about the internal structure and composition of these objects. These kinds of observations could help us better understand the life cycle of stars and the ultimate fate of objects like our own Sun. Looking even further into the future, the study of gravitational shadowing could have implications for our understanding of the multiverse, a concept that is currently speculative but has gained attention in recent years. The multiverse hypothesis suggests that our universe is just one of many, each with its own set of physical laws and constants. While there is currently no direct evidence for the existence of parallel universes, some physicists believe that the effects of gravitational shadowing might one day provide indirect evidence for their existence. If gravitational interactions between universes were possible, it might manifest as subtle anomalies in gravitational lensing or other gravitational effects. Though this is a highly speculative idea, it's an example of the kinds of groundbreaking discoveries that could emerge from the study of gravitational shadowing. Gravitational shadowing is also crucial in the ongoing search for dark energy, the mysterious force that is driving the accelerated expansion of the universe. Dark energy is one of the greatest enigmas in modern physics, and understanding its properties is one of the key challenges facing cosmologists today. Gravitational lensing has already been used to map the distribution of dark matter in the universe, and it's possible that gravitational shadowing could also provide clues about the nature of dark energy. By studying how light is affected by dark energy's influence on spacetime, scientists may be able to refine their models of this mysterious force and develop a deeper understanding of its role in the universe's expansion. As the tools and theories surrounding gravitational shadowing continue to evolve, it's clear that we are entering a new era of astrophysical discovery. With each breakthrough, we move closer to understanding the universe's most fundamental forces, from the nature of black holes and dark matter to the deepest questions about space, time, and the structure of reality itself. The mysteries are vast, but with each new piece of the puzzle, we inch closer to unraveling the cosmic riddles that have intrigued humanity for centuries. Gravitational shadowing, as we now know, is not just about observing shadows cast by massive objects. it's about understanding the complex dance of light, gravity, and time. As we continue to delve deeper into the mysteries of the universe, it's clear that the true impact of gravitational shadowing may yet be beyond what we can currently imagine. The knowledge we gain from studying this phenomenon holds the potential to revolutionize our understanding of everything from black holes and dark matter to the very fabric of space-time itself. One area where gravitational shadowing could have a significant impact is in the search for habitable planets outside our solar system, often referred to as exoplanets. As we continue to discover new exoplanets, we are faced with the challenge of determining whether any of these planets could support life. The conditions necessary for life are highly specific, and the detection of a planet's atmosphere and surface features is critical to identifying its potential for habitability. Gravitational shadowing can provide valuable clues in this search. For instance, when light from a distant star passes through the atmosphere of an exoplanet, the planet's gravity can bend the light in subtle ways. These distortions, detectable through gravitational lensing, may reveal important information about the planet's atmosphere and composition. This could help scientists identify planets with atmospheres that contain oxygen, water vapor, or other elements that are essential for life. As more advanced observational techniques become available, gravitational shadowing could serve as an essential tool in identifying exoplanets that are truly Earth-like in terms of their potential for supporting life. In fact, gravitational shadowing's role in detecting exoplanets is just one aspect of its broader impact on our understanding of the cosmos. As astronomers gain access to more powerful telescopes and instruments capable of measuring the gravitational effects of massive objects, they will be able to peer deeper into the universe than ever before. The next generation of space telescopes, such as the James Webb Space Telescope and the Nancy Grace Roman Space Telescope, will push the boundaries of what we can observe in the universe, opening new doors for the study of gravitational shadowing and lensing. But as promising as these advancements are, they also present new challenges. With the vast amount of data being generated by these telescopes, interpreting gravitational shadowing effects will become increasingly complex. Scientists will need to develop sophisticated algorithms and computational models to process and analyze the information, distinguishing subtle gravitational shadows from other sources of interference. These computational tools will be critical for unlocking the secrets hidden in the shadows, and as they continue to improve, they will allow us to make sense of an ever-expanding universe. At the same time, the study of gravitational shadowing could shed new light on the fundamental forces that govern the universe. While we have made significant progress in understanding the forces of gravity, electromagnetism, and the strong and weak nuclear forces, there are still many unanswered questions about how these forces interact. For example, the behavior of gravity on extremely small scales, such as within quantum mechanics, remains an unresolved issue. Some physicists believe that gravitational shadowing could provide key insights into this problem. By studying how gravitational fields bend light and distort the fabric of spacetime, scientists may be able to gain new perspectives on the relationship between gravity and quantum mechanics. Could gravitational shadowing provide indirect evidence of a quantum theory of gravity? It's possible that the phenomenon could offer a glimpse into how the large-scale structure of the universe interacts with the minuscule forces of quantum mechanics. This would be a monumental discovery in the field of theoretical physics, with the potential to unite two seemingly incompatible realms of science. Another fascinating aspect of gravitational shadowing is its potential to offer insights into the very origins of the universe itself. In recent years, scientists have been exploring the possibility that the early universe was filled with gravitational waves, ripples in space-time caused by the movement of massive objects. These waves, though incredibly faint, may have left subtle imprints on the cosmic background radiation that we observe today. By studying the way gravitational shadowing affects light from distant sources, scientists may be able to detect these ancient gravitational waves and, in doing so, unlock clues about the early moments of the Big Bang. In fact, gravitational shadowing could play a key role in testing some of the most intriguing ideas in cosmology. For example, the concept of the multiverse, while speculative, is gaining traction among some theoretical physicists. According to this hypothesis, our universe is just one of many in a vast, interconnected multiverse. While we currently have no way to directly observe other universes, some researchers believe that gravitational interactions between universes could create detectable effects, such as gravitational shadowing. If this idea is correct, studying the way light is bent by massive objects could reveal evidence of parallel universes, forever altering our understanding of reality. Moreover, gravitational shadowing could help us study phenomena that, while invisible to the naked eye, play an important role in shaping the universe. One example is dark energy, the mysterious force responsible for the accelerated expansion of the universe. While scientists have inferred the existence of dark energy from its effects on the cosmos, its nature remains a profound mystery. Gravitational shadowing could provide valuable clues about how dark energy influences space-time, and whether it is connected to other, as yet unknown, aspects of the universe. If we can observe how gravitational fields are affected by dark energy, we might gain a better understanding of its properties and role in the evolution of the universe. Despite the promise of these discoveries, we must also acknowledge the limitations of our current understanding. The universe is vast, and our ability to study gravitational shadowing is still in its infancy. As we venture further into the cosmos, we are bound to encounter new challenges and mysteries that will test the limits of our knowledge. The study of gravitational shadowing is not just about observing the effects of gravity on light. It is about unraveling the deepest secrets of the universe, from the nature of black holes to the structure of space-time itself. It is a journey into the unknown, one that will require patience, ingenuity, and a willingness to embrace the unknown. In the coming decades, we will likely see a surge in our ability to study gravitational shadowing. Advances in telescope technology, computational power, and observational techniques will all contribute to our growing understanding of how massive objects warp space-time, and how these effects can be detected from billions of light-years away. With each new discovery, we will take another step closer to unlocking the mysteries of the universe and perhaps gaining a deeper understanding of the forces that govern everything from the smallest particles to the largest galaxies. As we continue to explore the effects of gravitational shadowing, we may one day discover that the shadows cast by massive objects are not merely illusions, but rather, they are gateways to new realms of understanding, realms that could change the way we perceive the universe and our place within it. The future of gravitational shadowing is as vast and mysterious as the cosmos itself, and the journey of discovery has only just begun. Dark matter, by its very nature, does not emit, reflect, or absorb light, making it completely invisible to conventional optical instruments. Yet, its presence is felt through gravity. Gravitational shadowing provides a unique pathway to detect and map dark matter indirectly. When massive halos of dark matter bend the light from background galaxies, they produce distortions, sometimes dramatic arcs, sometimes subtle warps, that act as signatures of their presence. By studying these patterns, astronomers can reconstruct detailed maps of dark matter distribution in clusters and across cosmic scales. This ability to see the unseen has profound implications. It allows scientists to investigate how dark matter clusters, how it influences galaxy formation, and how it behaves differently from normal matter. One particularly groundbreaking application is in the study of colliding galaxy clusters, like the famous Bullet Cluster. Observations of gravitational lensing, essentially a type of gravitational shadowing, revealed that dark matter in the cluster had passed straight through the collision unaffected, while ordinary matter had interacted and slowed down. This difference in behavior is one of the strongest pieces of evidence for the existence of dark matter. Gravitational shadowing also plays a role in testing alternative theories of gravity. While Einstein's general theory of relativity has stood up to rigorous testing for over a century, it doesn't explain everything. Some physicists propose alternative theories, such as modified Newtonian dynamics, MOND, or emergent gravity, which attempt to account for dark matter-like behavior without invoking actual dark matter particles. Gravitational lensing and shadowing phenomena give researchers a direct way to test these ideas. If gravitational shadows deviate from predictions based on standard dark matter models, it could signal the need for a new framework entirely, perhaps even a rewriting of the laws that govern space and time. Beyond these grand cosmic scales, gravitational shadowing affects the precision of satellite navigation systems on Earth, such as GPS. These systems rely on extremely accurate timing to determine position. But gravity influences the passage of time itself, a consequence of general relativity. In regions where gravitational fields are stronger, time passes slightly slower. This means that signals sent from satellites experience tiny delays as they travel through the varying gravitational potential of Earth and the Sun. Even the Moon and planets exert minute influences. Accounting for gravitational shadowing, essentially the bending and delay of these signals through warp spacetime, is essential to maintain the precision of these systems, which we rely on for navigation, communication, and countless everyday applications. In particle physics and high-energy astrophysics, gravitational shadowing presents intriguing possibilities as well. When studying cosmic rays, high-energy particles that bombard Earth from space, researchers have noticed anomalies in their trajectories and energies. Some theories suggest that gravitational interactions with unseen masses or even micro-black holes could be at play, warping their paths in ways that mimic the lensing effects seen with light. If this is true, gravitational shadowing could help explain otherwise mysterious observations, like unexpected particle fluxes or directional biases in cosmic ray detectors. Even the birth of the universe, what we call the Big Bang, could have left gravitational imprints that continue to shape spacetime today. The cosmic microwave background (CMB), a faint glow left over from the universe's infancy, is remarkably uniform but contains slight fluctuations. These minute irregularities are influenced by gravitational waves and large-scale structures forming after the Big Bang. Gravitational shadowing alters how we perceive these fluctuations. Light from the CMB is bent as it passes through billions of light-years of evolving cosmic structures. Mapping the way these shadows are cast lets researchers decode how the first galaxies and clusters emerged from a near-uniform early universe. This has led to the rise of what's known as gravitational tomography, a technique that combines different gravitational lensing effects across multiple distances and directions to build a 3D map of mass in the universe. Much like a CT scan reconstructs an image of the inside of a body, gravitational tomography reconstructs a picture of the universe's hidden mass. Through it, scientists are attempting to track the history of cosmic expansion, the evolution of structure, and the roles that dark matter and dark energy have played over billions of years. Every insight gained from gravitational shadowing builds toward the broader goal of a unified cosmology, an all-encompassing model that explains where we came from, how the universe evolved, and what fate lies ahead. It connects the dots between the tiniest particles and the grandest galaxies, between fleeting light and the eternal curvature of spacetime. The power of this concept lies not only in its ability to illuminate what is hidden but in its capacity to challenge what we thought we already understood. By analyzing the light curves of pulsars, rotating neutron stars that emit beams of radiation, we can detect subtle gravitational lensing effects that reveal information about their mass, structure, and surrounding environment. These effects help scientists probe the internal composition of neutron stars, which remain some of the most mysterious and dense objects in the cosmos. Gravitational shadowing allows researchers to go beyond indirect observation and instead infer precise measurements of properties like mass-to-radius ratios, crust density, and even the existence of exotic states of matter such as quark-gluon plasmas. This is particularly crucial because conditions inside neutron stars cannot be replicated in any laboratory on Earth. They are natural laboratories of extreme physics, and gravitational shadowing acts like a cosmic CT scan, peeling back layers of mystery. Moreover, when these compact stars exist in binary systems, especially when paired with black holes or other neutron stars, the gravitational interactions become even more complex and revealing. Observing how light from a background star is affected as it passes near such binaries offers data-rich scenarios where the intricacies of general relativity can be stress-tested like never before. Gravitational shadowing also offers insights into the cosmic microwave background, the faint afterglow of the Big Bang that permeates all of space. Tiny fluctuations in this background radiation can be subtly altered by massive structures along the line of sight. These distortions, known as weak gravitational lensing or cosmic shear, represent another form of gravitational shadowing and serve as a powerful cosmological probe. By studying these patterns across vast regions of the sky, scientists can reconstruct the large-scale distribution of matter throughout the universe and gain deeper understanding of its rate of expansion and underlying geometry. In fact, this technique has helped refine measurements of key cosmological parameters, such as the Hubble constant and the density of dark matter. The precision with which gravitational shadowing can inform us about the early universe is unprecedented. It bridges the gap between the birth of the universe and its far future fate, acting as both a historical record and a diagnostic tool. A revised understanding of the universe's rate of expansion could indicate that new physics is at play, perhaps an unknown interaction in the early universe, a shift in dark energy's behavior over time, or the existence of yet undiscovered fundamental particles. Gravitational shadowing, by enabling precise mapping of how mass and energy are distributed across vast cosmic distances, helps refine the models we use to describe the universe's evolution. It acts as both a lens and a ruler, bending light in predictable ways while also providing a way to measure the distance and mass of intervening objects with extraordinary accuracy. One of the most exciting frontiers involves the synergy between gravitational shadowing and gravitational waves. When two massive objects like black holes or neutron stars collide, they send ripples through the fabric of space-time. These gravitational waves can be detected on Earth, but their source locations are often uncertain. If a gravitational wave passes through a region of space-time where strong gravitational shadowing is also occurring, it may be possible to correlate the shadowing effects on electromagnetic signals with distortions in the gravitational waveforms. This cross-analysis provides a fuller picture of the event and the objects involved, ushering in what scientists call multi-messenger astronomy. Multi-messenger astronomy leverages light, gravitational waves, neutrinos, and sometimes even cosmic rays to observe the universe from multiple perspectives. In this context, gravitational shadowing becomes a vital component, allowing us to decode how the gravitational field of an object alters every kind of signal passing through or near it. For example, when a gravitational wave event is accompanied by a visible gamma-ray burst or a kilonova explosion, gravitational shadowing of the light provides positional context while the gravitational wave supplies timing and mass details. Together, they tell a much more complete story of what happened, how massive the objects were, how fast they moved, and what kind of energy they unleashed. As observational technology continues to improve, scientists anticipate using gravitational shadowing in ways never before imagined. High-resolution space telescopes like the James Webb Space Telescope, or upcoming missions such as the European Space Agency's Euclid and NASA's Roman Space Telescope, will provide sharper and deeper images of gravitational lensing and shadowing effects across billions of light-years. These instruments are expected to identify thousands, if not millions, of new gravitational lensing events, each providing a unique probe into the universe's invisible framework. Gravitational shadowing, once a theoretical curiosity, is rapidly becoming a dominant tool in astrophysics and cosmology, with the power to test the limits of our most cherished theories and perhaps even point the way toward new ones. As instruments grow more sensitive and surveys expand, the role of gravitational shadowing becomes increasingly indispensable. Take, for instance, the Vera C. Rubin Observatory, which is set to begin operations with its Legacy Survey of Space and Time, LSST. This ambitious project will map the entire visible sky every few nights, creating an enormous dataset of billions of galaxies. With such vast coverage and depth, gravitational shadowing effects will be recorded in unprecedented detail. Researchers will be able to detect subtle distortions in the shapes of galaxies caused by intervening mass, offering a comprehensive map of dark matter across the universe. It's not just a step forward in observing gravitational shadowing. It's a leap toward decoding the invisible framework upon which the universe is built. Another exciting application lies in the realm of exoplanets. While gravitational shadowing is traditionally associated with massive objects on cosmic scales, its principles can also be applied in clever ways closer to home. Microlensing, a technique where a star or planet passes in front of a more distant background star, causing its light to temporarily brighten, is a manifestation of gravitational shadowing. This effect has already led to the discovery of many exoplanets, some even in regions of the galaxy where traditional transit methods would fail. These microlensing events, often detected by projects like OGLE, Optical Gravitational Lensing Experiment, or MOA, microlensing observations in astrophysics, depend entirely on shadowing mechanics, where the lensing object warps the light of the background star in a very specific way, revealing not only its presence but its mass and orbit. In the case of planetary systems, gravitational shadowing becomes a window into systems that may never transit their stars from our line of sight. This opens up the possibility of discovering rogue planets, worlds that drift freely through the galaxy without a parent star. These planets are notoriously difficult to detect, but if they pass in front of a distant star, the gravitational lensing effect can reveal their existence and mass. These rare detections offer unique insights into planetary formation and the dynamical processes that eject planets from their birth systems. Gravitational shadowing has also been instrumental in identifying and studying massive galactic clusters. These structures are often so massive that their gravitational fields distort entire regions of background space, creating arcs, multiple images of galaxies, or even complete Einstein rings, named after the very phenomenon predicted by his theory of general relativity. These dramatic displays of gravitational lensing are essentially extreme cases of gravitational shadowing, where light from a galaxy billions of light years away is bent into a ring or halo by the massive object directly in the path. By analyzing the geometry of these distortions, astronomers can determine the mass and distribution of dark matter in the foreground cluster, data that is otherwise inaccessible through direct observation. Furthermore, gravitational shadowing allows researchers to peer deeper into the early universe than ever before. Light from the earliest galaxies, just a few 100 million years after the Big Bang, is extremely faint and often redshifted into the infrared. However, when this light is magnified by intervening mass, thanks to gravitational lensing, it can become detectable with powerful telescopes like the James Webb Space Telescope, JWST. In this sense, gravitational shadowing acts like a cosmic magnifying glass, amplifying distant light and enabling us to study the properties of the very first galaxies, their star formation rates, and their chemical compositions. Without gravitational shadowing, many of these distant objects would remain hidden in the cosmic dark. The benefits of gravitational shadowing extend into the mysterious domain of dark matter and dark energy, which together account for about 95% of the total mass energy content of the universe. These components do not emit light, making them undetectable through traditional means. However, their gravitational effects, especially gravitational shadowing, are evident in how they bend the path of light from more distant sources. By meticulously mapping these lensing patterns across vast swathes of sky, scientists are constructing detailed dark matter maps. These maps are vital in testing models of dark matter distribution, whether it's cold dark matter, warm dark matter, or more exotic candidates. In addition to dark matter, gravitational shadowing helps constrain theories of dark energy, the mysterious force causing the acceleration of the universe's expansion. The shape, size, and frequency of shadowing distortions in large-scale surveys offer clues about how structures evolve over cosmic time. If dark energy's influence has changed over billions of years, it would be imprinted in the lensing data. Thus, gravitational shadowing doesn't just offer spatial insights, it also adds a temporal layer, giving us a window into how the cosmos has changed over epochs. On the theoretical front, gravitational shadowing is a critical testing ground for alternative theories of gravity. General relativity has passed every observational test to date, but physicists continue to seek a unified theory that merges gravity with quantum mechanics. Modified gravity theories, like F.R. gravity, MOND, modified Newtonian dynamics, or extra-dimensional models, make different predictions about how gravitational fields should behave. By studying how light bends in extreme environments and comparing it to predictions from various models, scientists can validate or rule out these competing ideas. Gravitational shadowing serves as a natural laboratory where the very fabric of spacetime is stretched, squeezed, and bent, revealing the deeper laws that govern the universe. We also find gravitational shadowing at play in the study of supermassive black holes and their environments. At the centers of most galaxies lie these titanic objects, millions or even billions of times more massive than the Sun. Their gravitational pull is so intense that it shapes the orbits of stars around them, draws in matter from accretion disks, and warps the light of nearby stars and gas clouds. With instruments like the Event Horizon Telescope, EHT, which famously imaged the shadow of the black hole in M87, we can directly observe the bending of light around the event horizon. That image, the glowing ring surrounding a dark void, is perhaps the most dramatic and visual example of gravitational shadowing ever captured. In such environments, gravitational shadowing also distorts the motion and appearance of nearby stars, sometimes producing strange orbits and apparent accelerations. These effects are used to estimate the black hole's mass and spin. Furthermore, as matter spirals into the black hole, it emits X-rays and gamma rays. The precise timing and shape of these emissions can be altered by relativistic effects, including shadowing, making them important diagnostic tools in high-energy astrophysics. Gravitational shadowing even affects our understanding of time itself. According to general relativity, time moves more slowly in stronger gravitational fields, a phenomenon known as gravitational time dilation. In the presence of massive objects, the warping of space-time caused by gravitational shadowing also includes a temporal component. This has practical implications for technologies like GPS satellites, which must account for both special and general relativistic effects to provide accurate positioning. Even slight discrepancies in timing caused by gravitational shadowing must be factored in, especially as satellite-based systems become more precise. As we move toward the future, gravitational shadowing promises to be central to many next-generation scientific missions. The European Space Agency's Euclid mission and NASA's Nancy Grace Roman Space Telescope are designed to map the universe's dark components using wide-field imaging and precise measurements of weak lensing. These missions will create enormous datasets, allowing for statistical studies of gravitational shadowing on an unprecedented scale. With AI and machine learning algorithms analyzing these data, we may uncover patterns and anomalies that lead to entirely new discoveries. Gravitational shadowing continues to reveal the universe's hidden structure, opening up possibilities for exoplanet discovery in ways we could never have imagined. Unlike traditional methods, such as detecting the dimming of a star's light as a planet passes in front of it, gravitational microlensing allows for the observation of exoplanets that don't pass directly in front of their stars, or may even be wandering alone in interstellar space. This makes gravitational shadowing a particularly potent tool for revealing rogue planets, those that drift through the galaxy without a host star. These elusive bodies are hard to detect through conventional means, but gravitational microlensing can spot them by observing the subtle way their mass bends and magnifies light from background stars. This method has already led to several remarkable discoveries. By studying these gravitational lensing events, astronomers can learn about the properties of the lensing objects themselves, their mass, size, and even their orbital dynamics, without ever needing to directly observe them. The ability to spot planets outside of traditional star systems also opens up questions about how planets form and whether planets can survive without a star, a concept that was previously thought to be impossible. As gravitational shadowing techniques continue to evolve, we are poised to discover even more hidden planets and possibly even entire planetary systems that were previously invisible. The next generation of telescopes, like the James Webb Space Telescope, promises to enhance our capabilities in this area, offering sharper images and more accurate measurements that will allow us to identify faint lensing events from distant objects with much more precision. These discoveries do not just deepen our understanding of planetary systems. They challenge our assumptions about how planets form and how they survive in different environments. The traditional view has been that planets form in the gas and dust surrounding stars, but gravitational shadowing opens up the possibility of planets forming in more diverse and surprising locations. Could rogue planets be remnants of stellar systems that were ejected during cosmic collisions? Could they have formed independently in the cold, dark regions of interstellar space? These are the questions that gravitational microlensing allows us to begin answering. As gravitational shadowing helps to map out the universe's structure, it also has profound implications for our understanding of cosmology. The phenomenon allows scientists to measure the mass distribution of galaxies and galaxy clusters with extreme precision. In fact, gravitational lensing is one of the best tools available to study dark matter. Because dark matter doesn't emit light or radiation, it cannot be detected directly by traditional means. However, its presence is evident through its gravitational influence on light passing through space. By observing the bending of light around galaxy clusters and mapping out the distortions caused by gravitational lensing, scientists can begin to infer the distribution of dark matter within these massive structures. This technique is critical in helping us piece together the nature of dark matter, which remains one of the biggest mysteries in modern physics. It's through these subtle, indirect observations that we come closer to understanding the unseen forces that govern the universe. The role of gravitational shadowing in our quest to understand dark matter is just one example of how this phenomenon is transforming the field of cosmology. In the future, as we develop more sophisticated tools and techniques for observing gravitational lensing, we may uncover new insights into the large-scale structure of the universe, its expansion, and the fundamental forces that govern it. The implications of these discoveries could redefine our understanding of space-time itself. Furthermore, gravitational shadowing is beginning to play a more prominent role in the study of black holes. The powerful gravitational fields around black holes create extreme conditions that distort light and time in ways that can be measured and studied. By observing the bending of light around black holes, scientists can learn about their size, spin, and mass, as well as the properties of the spacetime immediately surrounding them. The most dramatic example of gravitational shadowing in the study of black holes is the famous image of the black hole in the center of the M87 galaxy, captured by the Event Horizon Telescope in 2019. This groundbreaking achievement used the principles of gravitational lensing to produce the first-ever direct image of a black hole's event horizon, a glowing ring of light surrounding the dark core. The image itself is a testament to the power of gravitational shadowing, as the light from the accretion disk around the black hole was bent and warped by the black hole's immense gravitational field. The study of black holes through gravitational shadowing also helps to test the limits of general relativity. According to Einstein's theory, the warping of spacetime near a black hole should produce distinct observational signatures, including gravitational lensing. By measuring these distortions and comparing them with theoretical predictions, scientists can test the accuracy of general relativity in the extreme environments near black holes. This is critical in the ongoing search for a theory of quantum gravity, which seeks to reconcile general relativity with the principles of quantum mechanics. As we look to the future, gravitational shadowing will continue to be a cornerstone of astrophysical research. New missions, like the upcoming space-based gravitational wave observatories, will provide further opportunities to study the universe's most extreme objects and phenomena. These observatories, along with next-generation telescopes, will allow us to measure gravitational waves, map the distribution of dark matter, and observe the distant reaches of the cosmos in ways that were once thought impossible. Ultimately, gravitational shadowing will help us understand not only the invisible forces that shape the universe but also the very fabric of reality itself. It is a tool that bridges the gap between what we can see and what we can infer, allowing us to peer into the deepest, most mysterious corners of the universe. From the smallest exoplanets to the largest galactic structures, gravitational shadowing offers a glimpse into the forces that shape our universe, forces that are still largely hidden from our view. The beauty of gravitational shadowing lies in its ability to reveal the unseen, whether it's through the lens of dark matter, the mass of distant galaxies, or the existence of rogue planets. It is a reminder that the universe is not just a collection of visible stars and galaxies, but is also a complex and dynamic web of forces and structures that we are only just beginning to understand. With each new discovery, we get a little closer to unraveling the mysteries of the cosmos, and gravitational shadowing is one of the most powerful tools at our disposal to help us do just that. Gravitational shadowing has profound implications not only for understanding distant objects in the cosmos but also for advancing our knowledge of the fundamental laws of physics. One of the most exciting aspects of gravitational lensing, and specifically gravitational microlensing, is its ability to probe the unknown regions of the universe. We are beginning to grasp the intricacies of objects like rogue planets, whose existence challenges many long-held assumptions about planet formation. Gravitational shadowing has even opened new frontiers for searching for signs of extraterrestrial life. While we are far from directly detecting life on these rogue planets or distant exoplanets, the study of gravitational microlensing could potentially lead to insights about their habitability. Understanding the composition and conditions of these planets, including whether they have the necessary elements for life, is a step forward in the search for life beyond Earth. This new wave of discovery relies heavily on technological advancements that improve our observational capabilities. The next generation of telescopes is set to revolutionize how we observe gravitational shadowing and its effects. Instruments like the Nancy Grace Roman Space Telescope, which will be launched in the near future, will significantly enhance our ability to detect and study gravitational lensing events. These tools will allow scientists to collect more data than ever before, enabling them to identify lensing events with greater precision and across a wider range of cosmic distances. As a result, we can expect to see more detailed maps of galaxy clusters, the detection of more rogue planets, and perhaps the discovery of new phenomena that challenge the existing theories of astrophysics. In addition to improving detection capabilities, advancements in computational power are also playing a crucial role. Modeling gravitational lensing events requires vast amounts of data processing, as the interactions between light, gravity, and matter are complex and multifaceted. With the rise of machine learning and artificial intelligence, scientists are now able to analyze these enormous datasets with greater efficiency and accuracy. These technologies will not only speed up the process of identifying lensing events but also improve the precision of measurements, allowing for a more detailed understanding of the universe's structure and evolution. One of the most thrilling aspects of gravitational shadowing is its potential to help us explore the most extreme environments in the universe. We are talking about the enigmatic and exotic objects like black holes, neutron stars, and supermassive black holes that sit at the hearts of galaxies. These objects, which distort space-time to unimaginable extents, are often hidden from direct observation. However, the influence of their immense gravitational fields can still be felt, and through gravitational lensing, we can map out their properties. For example, studying the bending of light around supermassive black holes allows us to probe the regions near their event horizons. This gives us a better understanding of how these cosmic giants affect their surroundings and how matter behaves under such extreme conditions. Moreover, the recent observations of gravitational waves, ripples in the fabric of space-time caused by massive collisions, also offer another lens through which we can study the universe's most violent events. Gravitational lensing, in combination with gravitational wave detection, offers a powerful toolkit for investigating black holes and other compact objects. Beyond individual objects, gravitational shadowing offers a unique view of large-scale cosmic structures. Galaxies, clusters of galaxies, and the mysterious substance known as dark matter can all be studied through the lens of gravitational lensing. In fact, the distribution of dark matter in galaxy clusters has been inferred primarily through the bending of light from background galaxies. This provides critical insights into the role of dark matter in shaping the universe's structure. As we continue to refine our methods for observing gravitational lensing, we will be able to map out the distribution of dark matter with increasing accuracy and perhaps even uncover its true nature. Another fascinating area where gravitational shadowing plays a role is in the study of the expansion of the universe. By observing how light from distant galaxies bends and distorts as it passes through intervening galaxy clusters, astronomers can measure the rate at which the universe is expanding. This process, known as cosmological lensing, allows for more accurate measurements of the universe's expansion history and helps to refine our understanding of the cosmological parameters that govern the evolution of the universe. Even more intriguing is the idea that gravitational lensing could offer new insights into the nature of the universe itself. As we explore the universe's structure at large scales, scientists are also investigating whether our current understanding of gravity and spacetime is complete. Could gravitational lensing reveal signs of new physics beyond Einstein's theory of general relativity? Some theoretical models suggest that gravitational lensing could provide clues to the existence of extra dimensions or alternative theories of gravity. If true, these discoveries could fundamentally alter our understanding of the universe and its underlying principles. While the prospects of gravitational shadowing are immensely exciting, we must also be mindful of the challenges that come with it. The universe is vast, and the events that cause gravitational lensing are rare, which means that scientists must carefully monitor large portions of the sky over extended periods of time to capture these phenomena. In addition, the data generated by these observations can be incredibly complex and difficult to interpret, requiring sophisticated algorithms and computational tools. As a result, collaboration between astronomers, physicists, and computer scientists is essential to fully exploit the potential of gravitational lensing and gravitational shadowing. As the technology continues to advance, one can only imagine the remarkable discoveries that lie ahead. The continued development of space-based observatories, more powerful ground-based telescopes, and increasingly sophisticated data analysis techniques will undoubtedly lead to further breakthroughs. In fact, we may be on the cusp of a new era in astrophysics, where gravitational shadowing is not just a tool for discovering hidden objects, but a fundamental means of understanding the very nature of the universe itself. What is clear is that gravitational shadowing will remain at the forefront of astronomical research for the foreseeable future. It provides us with an unparalleled window into the cosmos, revealing hidden structures and offering new perspectives on familiar phenomena. Whether we are studying the formation of galaxies, the properties of black holes, or the distribution of dark matter, gravitational lensing will be instrumental in shaping our understanding of the universe. It is a reminder that, in the vastness of space, even the slightest bending of light can unlock the deepest mysteries of the cosmos. In the coming decades, as new missions are launched and our ability to detect and study gravitational shadowing improves, we are likely to witness a revolution in our understanding of the universe. The mysteries that have long eluded us, such as the true nature of dark matter, the fate of rogue planets, and the behavior of black holes, are poised to be unraveled. And as we explore these cosmic enigmas, gravitational shadowing will remain one of our most valuable tools for unlocking the secrets of the universe. As we delve deeper into the phenomena of gravitational shadowing, the applications extend far beyond just understanding the cosmos. The insights gained from studying these effects have practical implications for the future of space exploration and technology development. For instance, the study of gravitational lensing could lead to improvements in spacecraft navigation systems. Understanding how light behaves around massive objects could enhance our ability to maneuver spacecraft more effectively when navigating through regions of space with high gravitational gradients, such as near black holes or dense star clusters. Additionally, the effects of gravitational shadowing could have implications for communication systems. Signals transmitted across vast distances in space may be influenced by gravitational lensing, and understanding these effects could be critical for maintaining reliable communications with spacecraft exploring the outer reaches of the solar system. On a broader scale, the growing ability to detect and study gravitational lensing may inspire entirely new approaches to space missions. Future space missions may incorporate gravitational lensing as a tool to observe distant objects, especially those that are too far or faint for traditional telescopes. The concept of using gravitational lensing as a cosmic telescope has already been suggested, where massive objects like galaxy clusters are used as natural magnifying lenses to enhance the visibility of distant galaxies, stars, and exoplanets. This could allow us to observe phenomena that were previously beyond our reach, such as the formation of the earliest galaxies or the intricate processes that occur in the cores of supermassive black holes. One of the most intriguing aspects of gravitational shadowing is its potential to uncover hidden details about the universe's earliest moments. By studying gravitational lensing effects on light from distant galaxies, we can peer back in time to the early universe, offering us glimpses of a time shortly after the Big Bang. These observations could provide new information about the formation of galaxies, the distribution of dark matter, and the evolution of cosmic structures in the first few billion years of the universe's existence. This ability to look backward in time is a powerful tool that helps us piece together the puzzle of how the universe came to be, filling in the gaps that remain in our understanding of its origin. As we continue to study the effects of gravitational shadowing, scientists are also making progress in understanding the role of dark energy in the expansion of the universe. Dark energy, which is thought to make up a significant portion of the universe's total energy content, is still largely mysterious. However, gravitational lensing provides a way to measure its effects more directly. By analyzing how light from distant galaxies is distorted as it passes through the gravitational fields of galaxy clusters, astronomers can gain insights into the influence of dark energy on the large-scale structure of the universe. This research could be pivotal in determining whether dark energy is a constant force, or if it is changing over time, thus providing answers to some of the most profound questions in cosmology. In the realm of exoplanet research, gravitational lensing is already proving to be an invaluable tool. The ability to detect exoplanets via gravitational microlensing events has opened up new avenues for exploring planetary systems outside of our own. When a planet passes in front of a distant star, it can cause a temporary distortion in the light coming from the star. This microlensing effect is subtle but detectable, allowing astronomers to discover exoplanets that might otherwise remain hidden. This technique has been particularly useful for detecting planets that are not easily observable using traditional methods, such as those that are too far away or too faint to be detected through direct imaging or radial velocity measurements. What makes gravitational microlensing especially powerful is its ability to detect planets that exist in the habitable zone, the region around a star where conditions may be suitable for liquid water. By studying the lensing effects of stars in these regions, scientists can identify planets that might be capable of supporting life. While we are still far from being able to directly observe the conditions on these planets, the discovery of exoplanets in the habitable zone provides hope that we may one day find Earth-like worlds that are capable of sustaining life. The process of detecting and studying these exoplanets through gravitational lensing also brings us closer to answering one of the most fundamental questions in science. Are we alone in the universe? The search for life beyond Earth is one of humanity's greatest scientific endeavors, and gravitational lensing could play a crucial role in making that search more successful. As we identify more exoplanets in the habitable zone, we open the door to the possibility that life may exist elsewhere in the cosmos. Whether life on these planets is microbial or more complex remains to be seen, but the tools at our disposal, including gravitational lensing, bring us one step closer to answering this profound question. Despite the promising potential of gravitational shadowing, there are still challenges and limitations in fully utilizing this technique. One major challenge is the sheer complexity of interpreting the data. Gravitational lensing involves the bending of light from distant objects by intervening masses, and the resulting distortions can be subtle and difficult to analyze. Astronomers need to account for a variety of factors, including the mass and shape of the lensing object, the distance between the observer and the object being lensed, and the exact trajectory of the light. These variables can make it challenging to distinguish between different types of lensing events and to extract meaningful information from the data. Fortunately, advances in computational techniques and machine learning are helping to improve the accuracy of these analyses. Another limitation is the need for long-term observation. Gravitational lensing events are relatively rare, and they often occur over extended periods. This means that astronomers must continuously monitor large portions of the sky to catch these fleeting moments. In addition, many of the most significant lensing events are extremely faint, requiring highly sensitive instruments to detect them. As technology improves, however, we can expect these challenges to become less significant, and our ability to detect and analyze gravitational lensing events will continue to improve. Gravitational shadowing, particularly through microlensing, is also a powerful tool in the study of compact objects like black holes and neutron stars. These objects are often difficult to observe directly because they do not emit light. However, their gravitational fields can cause significant distortions in the light from background stars, making them detectable through lensing effects. Studying these objects via gravitational lensing not only helps us better understand their properties, but also provides insight into some of the most extreme environments in the universe. The information we gain from these observations could be key to unlocking the mysteries of black holes, such as their formation, growth, and role in galaxy evolution. Furthermore, as we improve our observational techniques and gather more data, we will begin to see more instances of strong gravitational lensing, where light from multiple distant sources is bent and magnified in dramatic ways. These events can reveal intricate details about the structure of galaxy clusters and provide further evidence for the existence of dark matter. In some cases, gravitational lensing can even create multiple images of a single object, offering a unique opportunity to study the same object from different perspectives. As we move forward, gravitational shadowing will continue to be one of the most important tools in the field of astrophysics. Its applications are vast and varied, ranging from the study of distant galaxies and exoplanets to the exploration of some of the universe's most extreme objects. With each new discovery, we are reminded of the universe's vastness and complexity, and how much there still is to learn. Gravitational lensing is opening new windows into this mystery, offering unprecedented views of the cosmos, and helping us answer questions that have captivated humanity for millennia. As the study of gravitational shadowing continues to advance, there is growing anticipation about how this phenomenon could enhance our understanding of cosmic events that once seemed beyond reach. Gravitational lensing is not just an extraordinary tool for astronomers. It also holds the potential to reshape our approach to numerous areas of physics and cosmology. With the development of more sensitive detectors and observational techniques, we are entering an era where the understanding of distant objects and events will be dramatically transformed. The idea of using gravitational lensing to view distant supernovae, for example, is a particularly intriguing prospect. These explosive stellar events, which mark the death of massive stars, can be some of the brightest objects in the universe. By observing how their light is distorted by intervening massive objects, scientists can gather information about the supernova itself, the nature of the galaxy in which it resides, and the properties of the lensing object. This emerging field of research is not confined to the observable universe. One of the most exciting potential applications of gravitational lensing is in the search for evidence of parallel universes or the multiverse. Although this idea remains speculative, some theoretical models suggest that gravitational lensing could provide indirect evidence for the existence of other universes. According to these theories, gravitational waves from distant universes could create subtle distortions in the fabric of space-time, which might be detectable through lensing effects. While this is still highly theoretical, it opens up new possibilities for exploration, and scientists are increasingly considering how gravitational lensing might be a key to unlocking the mysteries of other dimensions. The implications of these discoveries are profound. If we can detect subtle lensing effects from alternate universes or different regions of space-time, we may be able to test theories of quantum gravity and string theory. These ideas, which aim to reconcile quantum mechanics with general relativity, have long been on the fringes of physics, but gravitational lensing could provide the evidence needed to bring them into the mainstream. Such developments could fundamentally alter our understanding of the very fabric of reality. Additionally, gravitational shadowing has the potential to contribute significantly to the study of dark matter. As mentioned earlier, dark matter is a mysterious and invisible substance that makes up roughly 85% of the universe's total mass. It has been detected indirectly through its gravitational effects on visible matter, but scientists still have very little understanding of its nature. Gravitational lensing can help us probe the distribution of dark matter in galaxy clusters, offering clues about its density, shape, and how it interacts with visible matter. Since dark matter does not emit or absorb light, it cannot be observed directly. However, its presence can be inferred by observing how light is bent and distorted as it passes through gravitational fields created by dark matter. This method of studying dark matter has already provided valuable insights, and will likely continue to do so as we gather more data. As we gain a deeper understanding of gravitational shadowing, it is also important to explore the potential challenges associated with studying this phenomenon. One of the key obstacles is the complexity of the calculations required to interpret lensing events accurately. The light bending that occurs during gravitational lensing is influenced by a multitude of factors, including the mass, shape, and orientation of the lensing object. Additionally, The geometry of the lensing event can be extremely complicated, especially in the case of strong lensing, where multiple images of the same object are produced. Determining the exact characteristics of the lensing mass requires advanced models of general relativity and complex computational techniques. Moreover, the large-scale observations needed to detect these subtle distortions in light require significant resources and cutting-edge technology. Telescopes like the Hubble Space Telescope have provided invaluable data on gravitational lensing, but new instruments, such as the James Webb Space Telescope, will offer even more detailed observations. However, even with these advanced technologies, the sheer scale of the sky that needs to be surveyed means that many potential lensing events may go unnoticed. There is also the issue of competing factors that can cause similar distortions in light, such as the effects of foreground galaxies, which can mimic lensing effects and complicate analysis. Despite these challenges, the potential rewards of studying gravitational shadowing are immense. As our observational capabilities continue to improve, and as our understanding of the physics behind lensing deepens, we are poised to uncover new mysteries about the universe. The discovery of new exoplanets, the identification of previously hidden structures, and the exploration of dark matter and dark energy are just the beginning of what could be a revolutionary era in astrophysics. The ability to observe and study the effects of gravitational shadowing opens up a vast new frontier for scientific inquiry, one that promises to expand our knowledge of the cosmos in ways that were previously unimaginable. In the near future, we can expect to see even more exciting applications of gravitational lensing. One promising area of research involves using lensing to study the formation and evolution of galaxies. By examining the way light from distant galaxies is distorted by intervening clusters of galaxies, astronomers can gain insights into the conditions that led to the formation of these vast cosmic structures. In particular, gravitational lensing allows for the detailed study of the early stages of galaxy formation, providing a glimpse into the universe's infancy. Understanding how galaxies grow and evolve over time is crucial for developing a comprehensive theory of cosmology, and gravitational lensing is proving to be one of the most effective tools for answering these questions. Moreover, as we continue to push the boundaries of space exploration, gravitational shadowing may play an increasingly important role in the design of space missions. Future missions to distant parts of the solar system or beyond will encounter gravitational fields that could affect spacecraft trajectories, communication signals, and even the operation of instruments. By understanding how gravitational lensing and other related effects work, engineers and mission planners can design more efficient spacecraft that are capable of navigating complex gravitational environments. This could be especially important as humanity looks to explore more distant and extreme regions of space, such as the vicinity of supermassive black holes or the outer reaches of the solar system. The potential of gravitational shadowing is also being explored in the context of astrophysics and high-energy physics. The powerful gravitational fields near black holes and neutron stars can cause extreme distortions in space-time, offering unique opportunities to study these enigmatic objects. Gravitational lensing provides a means of observing the inner regions of black holes, which are otherwise hidden from view. By analyzing the light that is distorted and bent by these powerful gravitational forces, we can learn more about the nature of black holes, their growth, and their impact on surrounding matter. This research could help answer long-standing questions about the behavior of matter and energy under extreme conditions. Gravitational shadowing, whether through microlensing, strong lensing, or weak lensing, is one of the most promising areas of study in modern astrophysics. It provides a unique window into the universe, offering insights into everything from the nature of dark matter to the existence of exoplanets and beyond. As our observational technologies continue to improve, and as we develop better theoretical models to understand the complex phenomena at play, gravitational lensing will undoubtedly continue to shape the way we explore and understand the cosmos. The field is brimming with potential, and the next few decades will likely witness a revolution in our ability to observe, analyze, and interpret the universe's most enigmatic phenomena. Gravitational lensing, with its ability to reveal the hidden structures of the universe, has already proven itself as a crucial tool in the study of astrophysical phenomena. As more data accumulates from telescopes, satellites, and observatories across the globe, the scope of gravitational lensing's applications continues to expand, offering new perspectives on previously intractable problems. In particular, lensing is increasingly seen as an essential method for testing our fundamental understanding of general relativity and quantum mechanics. One of the central tenets of Einstein's theory is that gravity is the warping of spacetime by mass and energy. Gravitational lensing provides a natural laboratory for testing this idea, allowing scientists to study how light behaves when it encounters massive objects, and to measure the effects of these distortions in minute detail. What makes gravitational lensing especially unique is its versatility. Unlike other observational techniques that may only be applicable under specific conditions, lensing can be used to probe a wide range of phenomena, from the most massive galaxy clusters to the faintest background sources. For example, gravitational lensing has been used to study the most distant galaxies, allowing scientists to examine their properties and structures at epochs long past. By using lenses, astronomers can bypass the limitations of our observational instruments and look deeper into the past than ever before. A key area of interest in the study of gravitational lensing is the determination of the expansion rate of the universe. The Hubble constant, which describes the rate at which the universe is expanding, has been the subject of much debate and uncertainty. Different methods for measuring this constant have produced conflicting results, but gravitational lensing has the potential to resolve this discrepancy. By analyzing the time delays between multiple images of a lensed object, astronomers can determine the distance to the object with greater precision. Combining this with other observational techniques, such as the measurement of the cosmic microwave background radiation, could help settle the debate over the true value of the Hubble constant. Moreover, gravitational lensing is not just a tool for studying distant objects, but also for understanding the local universe. It can be used to examine the distribution of dark matter within our own galaxy, as well as the mass and structure of galaxy clusters. These applications are particularly important because dark matter, which makes up the majority of the universe's mass, has remained largely invisible to traditional forms of observation. By measuring the bending of light from background sources, scientists can infer the amount of mass present in galaxy clusters and determine how this mass is distributed. This is crucial for understanding the role of dark matter in the formation and evolution of cosmic structures. Another exciting aspect of gravitational lensing is its potential to detect and study exoplanets in ways that were previously impossible. Exoplanets are planets that orbit stars outside our solar system, and detecting them has been one of the major goals of modern astronomy. While many exoplanets have been discovered using methods such as the transit method and radial velocity, gravitational lensing offers a completely different approach. When an exoplanet passes in front of its host star, the gravitational field of the planet can cause a temporary brightening of the star's light. This effect, known as microlensing, can be used to detect exoplanets that might otherwise be invisible to traditional methods. The ability to detect exoplanets through gravitational lensing could have profound implications for the search for extraterrestrial life. Not only would it enable astronomers to discover new worlds, but it could also provide valuable information about the conditions on these planets. For example, microlensing events can be used to determine the size and composition of exoplanets, as well as their distance from their parent stars. These factors are critical for assessing whether a planet could potentially support life. Additionally, by studying the lensing effects caused by distant exoplanets, scientists can learn more about the nature of planetary systems and how they form. One of the most intriguing possibilities opened up by gravitational lensing is the potential for detecting hidden black holes. These objects, which are defined by their incredibly strong gravitational fields, are typically invisible to direct observation. However, the gravitational influence of a black hole can distort the light from background sources, creating a lensing effect. By carefully studying these distortions, scientists can detect the presence of black holes that would otherwise remain undetected. This is especially important for understanding the role of black holes in the evolution of galaxies and the universe as a whole. In particular, supermassive black holes, which lie at the centers of most large galaxies, are thought to play a crucial role in galaxy formation and evolution. Gravitational lensing may be the key to unlocking the mysteries of these enigmatic objects. Furthermore, as we look ahead to future space missions, gravitational lensing is likely to play an even greater role in the exploration of distant regions of the cosmos. The upcoming James Webb Space Telescope, for example, will be able to study distant galaxies in unprecedented detail, using gravitational lensing as a tool to probe the early universe. By observing how the light from distant galaxies is bent and stretched by intervening objects, astronomers will be able to study the formation of galaxies in the first few billion years after the Big Bang. This will provide crucial insights into the processes that led to the formation of the first stars and galaxies, as well as the role of dark matter in these early stages of cosmic history. In addition to the James Webb Space Telescope, other upcoming missions, such as the Euclid Space Observatory, are set to make significant contributions to the study of gravitational lensing. Euclid, which is scheduled to launch in the near future, is specifically designed to study the geometry of the universe and the distribution of dark energy. One of its primary goals is to use gravitational lensing to probe the expansion of the universe and the nature of dark energy, which is thought to be responsible for the accelerating rate of expansion. By combining data from Euclid with other observational techniques, scientists will be able to test different theories of cosmology and gain a deeper understanding of the universe's evolution. As exciting as these developments are, it's important to recognize that there is still much we don't know about gravitational lensing and its full range of applications. For example, one of the biggest challenges in the field is understanding the role of smaller, less massive objects in lensing events. While much of the research on gravitational lensing has focused on massive galaxy clusters or black holes, smaller objects such as rogue planets or dark matter halos may also have a significant impact on the way light is bent and distorted. These objects, which are difficult to detect directly, could be responsible for subtle lensing effects that are currently beyond the reach of existing instruments. To fully harness the potential of gravitational lensing, scientists will need to develop new techniques for analyzing the vast amounts of data generated by these events. This will require advanced computational methods, as well as improvements in the resolution and sensitivity of observational instruments. Machine learning, for example, has already shown promise in identifying and classifying gravitational lensing events, and it is likely to play an even greater role in the future. By using artificial intelligence to sift through large datasets, astronomers may be able to identify previously unknown lensing events and uncover hidden patterns in the universe. The study of gravitational lensing is poised to revolutionize our understanding of the cosmos. From probing the nature of dark matter to discovering exoplanets and hidden black holes, gravitational shadowing offers an unprecedented window into the universe. As observational technologies continue to improve and our understanding of gravitational physics deepens, the potential for new discoveries is virtually limitless. Gravitational lensing is not just a fascinating phenomenon, it is one of the most powerful tools available to astronomers and physicists, and it will continue to shape the future of space exploration for years to come. As gravitational lensing continues to push the boundaries of our understanding, one of the most intriguing aspects of this phenomenon is its ability to provide insights into the fundamental nature of the universe itself. The observation of gravitational lensing effects is not merely a tool for studying distant galaxies or the distribution of dark matter. It also offers a profound opportunity to test the limits of Einstein's theory of general relativity, the cornerstone of modern gravitational physics. Despite its overwhelming success in explaining a wide range of astrophysical phenomena, general relativity has its limitations, and gravitational lensing provides a natural laboratory for testing its predictions. One area where gravitational lensing is proving invaluable is in the study of gravitational waves. These ripples in spacetime, predicted by Einstein over a century ago, were only directly observed for the first time in 2015. Gravitational lensing plays a role in this field by enabling the detection of gravitational waves from sources that would otherwise be too faint or too distant to observe. For example, gravitational lensing can magnify the signals from merging black holes or neutron stars, making them easier to detect. This ability to enhance the visibility of these elusive waves could open up entirely new ways of studying extreme astrophysical events, and may eventually lead to the detection of gravitational waves from the earliest moments of the universe. But gravitational lensing's contribution to our understanding of the cosmos doesn't stop there. One of the more exciting frontiers of this research lies in its potential to provide insights into the nature of dark energy, the mysterious force driving the accelerated expansion of the universe. While the effects of dark energy are observable on the largest scales, the exact nature of this force remains one of the greatest unsolved puzzles in physics. Gravitational lensing may hold the key to understanding dark energy's behavior across different epochs of the universe. By observing how the lensing effects change over time, scientists may be able to discern patterns that could reveal more about the properties of dark energy and how it interacts with spacetime. On a more theoretical front, gravitational lensing also challenges our understanding of the very fabric of spacetime itself. In Einstein's theory, mass and energy warp spacetime, bending the path of light as it passes through this curvature. However, some alternative theories of gravity, such as those involving extra dimensions or modifications to general relativity, make different predictions about how light should behave when it passes near massive objects. By studying the subtle variations in gravitational lensing effects, scientists can test these alternative theories and potentially identify signs of new physics. This is particularly exciting because it could provide insights into the deepest questions about the nature of space, time, and the universe as a whole. In addition to its theoretical implications, gravitational lensing has a more practical impact on the field of cosmology. The study of lensing can help scientists measure the mass of galaxy clusters and map their distribution across the universe. This is critical for understanding how large-scale structures in the universe form and evolve over time. By examining the distortions in light caused by massive galaxy clusters, astronomers can calculate their total mass, including both visible and invisible components, such as dark matter. The study of lensing thus provides a powerful tool for mapping the large-scale structure of the universe, offering insights into how galaxies, galaxy clusters, and superclusters are distributed across space. Gravitational lensing also plays a key role in the study of galaxy formation and evolution. By observing the way light is bent by intervening galaxies and galaxy clusters, scientists can examine the properties of these objects and trace their development over cosmic time. Lensing allows astronomers to probe the interiors of galaxies that would otherwise be too distant or too faint to study in detail. For example, lensing can reveal the distribution of gas, dust, and stars within a galaxy, shedding light on the processes that govern galaxy formation and the mechanisms that drive their evolution. These observations can help to answer fundamental questions about how galaxies form, grow, and interact with one another over billions of years. In the search for exoplanets, gravitational lensing holds the promise of unlocking new discoveries that would otherwise be impossible. While traditional methods for detecting exoplanets, such as the transit method and radial velocity, have been successful in identifying thousands of planets around distant stars, these techniques have limitations. Gravitational lensing, on the other hand, offers a different approach that can detect exoplanets in ways that other methods cannot. The phenomenon of microlensing, for instance, occurs when the gravitational field of a star or planet causes a temporary brightening of a background star. This effect can reveal the presence of an exoplanet, even if it is too small or too far away to be detected by other means. By studying microlensing events, astronomers can detect new exoplanets, providing crucial information about the diversity of planetary systems across the galaxy. One of the most exciting aspects of using gravitational lensing to discover exoplanets is the potential to find Earth-like worlds in the habitable zone of distant stars. These are planets that are situated at just the right distance from their parent star to allow for liquid water to exist on their surface, one of the key ingredients for life as we know it. While the search for Earth-like exoplanets is ongoing, gravitational lensing may provide a more efficient method for detecting these elusive worlds. By identifying microlensing events caused by planets in the habitable zone, astronomers could uncover new candidates for future study, potentially increasing the chances of finding alien life in the universe. The study of gravitational lensing also holds promise for the search for primordial black holes, objects that are thought to have formed in the very early universe. These black holes, which are believed to be smaller and less massive than their stellar counterparts, could potentially account for some of the mysterious dark matter that permeates the cosmos. Gravitational lensing could provide a way to detect these primordial black holes by observing the way they distort the light from background sources. If such black holes exist, their presence could have a significant impact on our understanding of the early universe and the formation of the first structures after the Big Bang. Gravitational lensing also plays a crucial role in the study of the cosmic microwave background, CMB, the faint afterglow of the Big Bang. By examining how the CMB is distorted by the gravitational fields of galaxy clusters and other large structures, scientists can gain insights into the early universe and the processes that led to the formation of galaxies, stars, and other cosmic structures. These distortions, known as the integrated Sachs-Wolf effect, are subtle but can provide important clues about the properties of dark matter, dark energy, and the evolution of the universe as a whole. As we look ahead to the future of gravitational lensing research, one of the key challenges will be developing new technologies and techniques to enhance the precision of lensing measurements. While current telescopes and observatories have made significant strides in this area, there is still much to be done to improve our ability to detect and analyze gravitational lensing events. Advancements in imaging technology, for example, could allow astronomers to study lensing effects with greater resolution, revealing finer details of the underlying structures that cause these distortions. In addition, the development of more sophisticated computational models and data analysis techniques will be essential for extracting meaningful information from the vast amounts of data generated by lensing events. The study of gravitational lensing is transforming our understanding of the universe in ways that were once thought to be impossible. From unveiling the mysteries of dark matter and dark energy to discovering exoplanets and testing the limits of general relativity, gravitational lensing offers a unique window into the cosmos. As our observational tools improve and our understanding of gravitational physics deepens, the potential for new discoveries continues to grow. Gravitational lensing is not only one of the most powerful tools available to astronomers today, but it is also one of the most exciting frontiers in modern science, offering a glimpse into the deepest mysteries of the universe. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.